Rosemary Harris from Queen Mary University in London. She's going to speak about insight from non-Markovian random walks. I want to remember the speaker that she has 25 minutes for the talk plus 5 minutes for discussions. Please.
Good morning. So hopefully you can see and hear me and see my screen okay. Thank you very much for the introduction and for the invitation. It's very nice to be here, albeit virtually. So I'm going to tell you about some statistical physics insights from simple non-Markovian random walks, and in particular, some applications to decision modeling, which fit within the complex systems side of this very nice meeting. So I appreciate that it's first thing in the morning. It's even earlier here in the UK, because you know we like to be different to the rest of Europe. So we're going to start very, very simple. So simple that we could almost be in this book, Statistical Physics for Babies. We're going to start by thinking about Markovian random walks. And perhaps the simplest kind of Markovian random walks in one dimension and discrete time. So that means that we have the position at time t plus 1, which is just the position at time t, plus some step length or noise, where the step lengths are independent, identically distributed random variables. And of course, the most familiar example is perhaps the case where the step lengths are +1 with some probability, let's call it p plus, and -1 with probability p minus. And then you just have a random walker on a one-dimensional lattice that goes to the right and left with different probabilities. And even this uber simple model can be thought of as a kind of trivial model of decision making. If you imagine somebody repeatedly making a decision with no memory of what they did before and just making the decision randomly, so tossing a bias coin, they perhaps have some vague idea that one of the choices, let's say to move to the right, is better than the other, so they're more likely to take that, but they're just making a random decision at every time step. That, of course, is not how we make decisions, even early in the morning. And Markovian random walks are not really what we're interested in statistical physics. So now we're going to try and add some memory. And the idea is to add memory to these simple models, both to help illuminate some general principles of non-Markovian statistical mechanics, but also to give insight into perhaps slightly more realistic decision modeling. But as soon as I say I'm going to add memory, you probably think, well, how? What kind of memory? There are probably as many different ways to add memory as there are people working in the field. You could think, for example, of having some kind of hidden Markov process with latent variables or internal states. Or you could think of your favorite reset renewal model with non-geometric times between the renewals. And that, of course, can be related to run and tumble type processes of the type we already heard a bit about yesterday. So lots of different ways to think about non-Markov random walks, even in one dimension. I'm going to focus on just one class of processes, a class of processes where the step distributions, or more generally the transition probabilities, depend on the time average velocity, or if you like, the current of the particle up to that point. So they depend on the whole history of the random walk, albeit in quite a simple way. And by sort of zooming in on this class of processes, I'm going to try and tell you two things in the time I have this morning. First, and quite briefly, I'll say something about fluctuation mechanisms in systems with long-range memory, and that's joint work with Rob Jack in Cambridge. And then for the majority of the talk, I'll focus on this application to decision-making with distorted memory, which is based partly on some slightly older work, and then on this rather recent preprint. So on to the first part. This is really a tale of two elephants. The first elephant is quite a famous non-Markovian random walk, the so-called elephant random walk. elephants never forget. So an elephant random walk introduced in 2004 is a random walker which remembers its whole history, its positions in discrete space, and the probability of going right or left at the next step depends on the fraction of steps right or left in the past. In particular, we have some memory parameter A, and if the value of the velocity up to the time we're at is vt, the next step is right or left with the probabilities you see here. So we'll concentrate on the case where A is positive, and that means we have a kind of positive reinforcement. So if the velocity is positive in the past, the random walker is more likely to go to the right in the future, and similarly for negative. So that's the standard elephant random walk. The second elephant that Rob and I considered is a variant of that, really, which we call the Gaussian elephant random walk. This has a position in continuous space, and if the value of the velocity up to the time we're at is vt, then the next step is from a Gaussian distribution, clues in the name, with mean AVT and variance 1. So you perhaps already spot that these models look very similar. The mean step length is the same in both of them, and the variance is the same in both of them. But we'll see there are some important differences. Let's first of all think about the typical behavior. Let's consider a kind of conditional expectation that I'll call delta. That's the mean displacement for the t+1 time step, assuming we have velocity vt so far. Then you can see relatively straightforwardly that you expect kind of mean typical trajectories to be given by the following discrete mapping. So the velocity at time t+1 related to the velocity at time t and this delta function. And from there, you get that fixed points satisfy the obvious condition that at a fixed point, the expected displacement at the next step, so delta is kind of instantaneous velocity, if you like, is the same as the velocity in the past. And as usual with fixed points, you can consider their stability by looking at the slope of this function delta v. So you have a kind of cobweb construction, which shows you that if the derivative of delta v is less than 1 at the fixed point, you have a stable fixed point. And if it's greater than 1, you have an unstable fixed point. For both the elephant random walk and the Gaussian elephant random walk, then this delta function is just a times the velocity. So the fixed point is trivially 0. And if a is less than 1, then it's stable. So in the long time limit, the velocity converges to 0 in both models. Now we want to think about fluctuations to see velocities away from 0. And generally they involve excursions at the start of the trajectory because there's less probabilistic cost for an excursion there. And I'm just going to focus in now on the case where a is greater than a half, where the memory effect is strong in some sense. I can say something about other regimes if you're interested. So a is greater than a half and less than 1. The elephant random walk, the original elephant random walk, can be treated as a polyurn. It is a kind of polyurn, so you can use results of Franchini, and you can find the asymptotic distribution of the velocity, which has this exponential form. And for those who are familiar with these things, this is, of course, just a large deviation principle with speed t, but with some slightly weird rate function that's non-analytic for general values of a. So the memory here has introduced a non-analyticity into the rate function. The Gaussian elephant random walk is much easier to analyze because it's Gaussian. You basically end up just summing Gaussian displacements, and you can find, again, the asymptotic distribution of the velocity. But this looks rather different. It's again a large deviation form. The rate function is well behaved, it's just quadratic. But now you have a different power of t. So this is a large deviation principle with a modified speed, which was also found in some earlier work and various things since then. So what's the difference between these two models? Why do they have such different fluctuation behavior, even though their typical behavior is the same? Well, this relates actually to something we heard about in the very first talk of the conference. It's sort of connected to this idea of a big jump. So in the elephant random walk, each step can't be larger than 1. So if you want to have a fluctuation above the average, what happens is that you have a macroscopic fraction of the steps at the beginning of the trajectory with step length close to 1. So you have lots of steps a bit above the average, if you like. On the other hand, for the Gaussian elephant random walk, the step lengths can be arbitrarily long. So the cheapest way to achieve a fluctuation away from the average is to have just a few steps at the beginning that are absolutely huge, and then to decay with the natural dynamics of the process. And we call this an initial giant leap, but actually it's related to this big jump idea. And these two generic mechanisms, a long initial excursion and an initial giant leap, are found in other models too, and we were able to give conditions for when you'd see these different kinds of mechanism in different kinds of non-Markovian models, also including many particle models. But let me leave that now and return in the last 15 minutes or so to the decision making. So how do we actually make decisions? Well, it's very complicated, but part of it relates to this idea in economics of utility, which goes back to the greatest happiness principle of Jeremy Bentham. Here's Jeremy Bentham. His body is famously at UCL. This is the picture I used to show of him, but actually he moved just before the first COVID lockdown, and he now sits in this box on the right in the Student Inquiry Centre at UCL, nicely COVID secure behind a glass screen. Anyway, apart from leaving his body with these slightly eccentric instructions, he formulated this idea of a greatest happiness principle, which is the idea that human beings make decisions in a way that maximizes their happiness. And that's the sort of forerunner of what we now call utility, which you can think of as a measure of reward or satisfaction or benefit you get from making a decision. And the idea is that if you're totally rational, you weigh up the utility for different decisions and you pick the decision with the highest utility. Of course, we're not totally rational. One thing is there's quite a lot of noise in our decision making, and we'll see that later. But the other thing is that the utility we use in our decisions might be quite different from the utility we actually experience when we make those decisions. And part of the reason for that is that we misremember things. Our memory is distorted. And one way that our memory is distorted relates to this psychological heuristic called the peak end rule. So I'm going to tell you about that, and then we'll see eventually how it connects to the kind of models we were thinking at in the beginning of the talk. So the peak end rule is famously worked by Daniel Kahneman, who got the Nobel Prize for economics. And what he and his co-workers did in the original experiments, they didn't look at happiness or benefit, but they looked at pain during colonoscopies. So they took a bunch of patients who I'm told had to have colonoscopies anyway, and they didn't have general anesthetics. They were awake but mildly sedated, and they asked the patients at every minute during the procedure how horrible it was. And then they plotted these graphs of pain against time. And then at the end, when it was all over, they went back to the same patients and they asked them to retrospectively evaluate it, to give a single number saying how terrible their experience was. And what they found was that they could predict very well this retrospective evaluation just by taking a straight mean of the peak, the worst bit of the experience, and the end. So we might look at these graphs and say, well, this is pain against time. So clearly patient B had a worse time because they've got more integrated pain. But it turns out in real life, it's not like that. Really, at least in this case, it's just the peak and the end that play a role. The length of the experience didn't seem to matter very much. It's called duration neglect. And in fact, they tested this, apologies to those who are still eating their breakfast, by keeping the probe inside people longer than was necessary, but making the end bit a little bit more gentle, so giving them some extra pain, and people went away happier. So I think one of these papers is called When More Pain is Preferred to Less. And since then, the peak end rule has been tested in different scenarios, happier scenarios, how you remember holidays, for example, with the idea being that you remember the best bit and the journey home, perhaps, how people evaluate movies, and various other situations. And I would say that in some cases it seems to work well, in some cases it works a bit less well. But what is true and is evident is that as humans, we don't remember everything. We don't just remember the most recent things. We don't have some kind of smoothly decaying memory kernel, but actually we remember particular snapshots, particular episodes, and in particular, we remember extremes. So our aim was to investigate how memory at the peak, we'll ignore the end for now, affects future decisions. So here's the decision model, which I already hinted at earlier. We have a single agent repeatedly deciding between plus and minus choices, right and left, if you like, so a one-dimensional random walk. And we count the number of plus choices up to time t and the number of minus choices up to time t and call those capital X. In fact, it's generally easier to consider the fractions, which are, of course, sort of velocities right and velocities left. So far, so boring. The new ingredient now is that we model this utility. Every time the agent makes a choice, we draw a value of a utility random variable, an experience random variable, from some distribution that might be different for the right choices and for the left choices. And the idea is that the agent doesn't remember all of those values of the utility. They just remember the maximum for the right choices, the plus choices, and the maximum for the left choices. And I'll call those things U hat plus and U hat minus. So remember that the hat is the peak, is the maximum. And it's that peak that goes into the probabilities for what happens next. So the probabilities for going right and left are now themselves random variables, capital P plus and capital P minus. And I take what economists call a logit form, but perhaps is familiar to us because they look like Boltzmann distributions, where the T that appears here can be thought of as a kind of social temperature or a level of noise. So let's just look at that a little bit more closely. Here it is again at the top. And let's see that it makes sense. If capital T is very big, if the noise is very big, then both these probabilities are approximately a half. In other words, there's really no memory in the process. It's just a random walker, somebody making random decisions. On the other hand, if the noise is small and positive, then there's a bias in the direction of whichever is bigger, U hat minus or U hat plus. So you tend to go in the direction where you remember, in this distorted way, having the best experience. So let's see what happens. First of all, let's look at the case where we have two choices with the same utility distributions, homogeneous choices. Notice that that doesn't mean that the distributions of U hat plus and U hat minus are the same at any moment in time, because they will depend on how many steps the agent has made right or left in the past. What happens then in the long time limit? Well, perhaps you can convince yourself that there are a couple of things that might happen. Perhaps you might say, well, the problem is a priori symmetric, so what I expect to happen in the long time limit is that U hat plus will be asymptotically the same as U hat minus. Both the probabilities will be about half. A fraction of half the steps will be right, half will be left. I'll be in a kind of mixed decision state where the agent is sampling both choices. On the other hand, perhaps it's possible that somehow early on you have a particularly good experience, let's say for a rightward step, and then you're more likely to go right and you're more likely to have an even better experience. So perhaps you can sort of get sucked into a fixed point where asymptotically you only go right, or of course asymptotically you only go left. And that corresponds to a kind of frozen decision state where you're sort of trapped by habits, you're trapped by your past experience. And indeed we see these things. So on the right, I plot simulation results showing the empirical histogram of velocity after 100 time steps with an exponential distribution of utilities for both right and left steps. And in green, you have a high value of the noise. and you see the distribution is peaked around 0. And so the symmetric fixed point. And in red, you have a low value of noise, and you see the distribution is peaked around -1 and +1. So this frozen state where you're only going right or only going left. And the question then is, well, how does this picture depend on the details? How does it depend on the level of noise, and in particular on the distribution of the utilities? Well, that's quite hard in general, but there's a sort of shortcut, a simplified model, which turns out to give quite useful information. And the idea is that we approximate the random variables for the maximums, u hat plus or minus, by the so-called characteristic largest value after x plus steps right and x minus steps left. So that comes from extreme value theory. You just say, well, if I've made x plus trials of a random variable, what typically will be the largest value of that random variable I see? And you can get those characteristic largest values directly from the CDFs. And if you do that, then the probabilities for going right and left are now no longer random variables, they're deterministic functions of the number of steps right and left in the past, or equivalently of the velocity and time. So this is now back in the class of a generalized elephant random walker or a Polya-Earn problem. And you can play exactly the same games that I showed you earlier and solve for fixed points and check their stability. And I won't show you the details, but if you know anything about extreme value theory, you perhaps won't be surprised, and hopefully this will answer the question I see in the chat from Sumida, what decides if the fixed point will be symmetric or asymmetric for large values of time. So you have 3 generic classes that come from extreme value theory. If your utility distribution has fat tails, like a Pareto distribution, for example, then it turns out that the symmetric fixed point is always unstable for long enough times. In other words, what happens is that the agent has a very good experience in one direction, they're more likely to go in that direction, more likely to get an even better value of the utility, and overwhelmingly end up going one way or the other. So if you have a fat-tailed utility distribution, that's what this simplified model predicts. And simulations looking at the root mean square of the velocity in the real model bear this out, that for large values of time, you end up with a variance of 1, so in plus minus 1. On the other hand, if your utility distribution is bounded, like a uniform distribution, then the symmetric fixed point is always stable for long enough times. There might be some early metastable behavior, but eventually the agent will have seen effectively the maximum for right choices and left choices, and then we'll be back to symmetric random walk, and you'll end up in the symmetric fixed point. So with a variance going to 0 for long times. The interesting case, as I hinted at before, is the case of exponential tails. Then you really do have a transition from a frozen state for low values of noise to a mixed state for high values of noise, possibly with some logarithmic dependence on time. So this simplified model suggests that for homogeneous choices, if you have fat-tailed utility distributions or exponential utilities with low noise, you have a kind of ergodicity breaking, a trapping, where the time average velocity for a specific agent is not the same as the ensemble average. If you're in this red situation, then a specific agent will have time average velocity -1 or +1, but the ensemble average will be 0. But it doesn't matter, because in this homogeneous case, all the choices have the same average value of the utility, so it doesn't really matter whether or not you're trapped. It becomes much more serious in the case of heterogeneous choices, which has basically been the PhD work of this guy who's just finishing up now, Vangelis Mitsokapas. And the question then is, how can we escape trapping in the wrong choice? How can we avoid the case that we're deluded by some early experience and end up trapped in a choice which has lower expected utility? So very briefly, let me show you simulations of the time and ensemble average utility for the case where you have an exponential utility for right steps with parameter 2, so mean 1/2, and for left steps with mean 1, So in this case, the left step, the minus choice, is the better one. And I plot here the average utility against noise for both the simplified model and the full model, so the real model. And what you see is that the qualitative features are rather similar. And in both cases, as noise goes to 0, or as noise goes to infinity with finite time, the average utility has this rather simple form, which evaluates to 0.75 here. And the reason for that is that as noise goes to 0, an individual agent makes its first choice with probability 1/2 for each direction, and then does the same forever after. So the ensemble average is 0.5 times 1 over lambda plus 0.5 times 1 over lambda minus. On the other hand, in the high noise limit, we're back to the case where each agent samples both choices equally. So both for an individual agent and for the ensemble, the average is 0.75. But in the middle, there appears to be a peak that's somewhere around 1 over lambda plus. And I know I'm almost out of time, so in the last minute or so, let me tell you something about that peak by concentrating on the simplified model. You no longer have fixed points, but you have a kind of dynamical landscape picture, which predicts 3 different regimes. A low noise regime, where you still have this trapping. An intermediate noise regime between these 2 dashed lines, where as time goes to infinity, you eventually saturate, you eventually escape the bad trap and end up in the good trap. And you can predict that the way you saturate is as 1 over time with a log correction, and check that with simulations. And then a high noise regime, so to the right of 1 on the plot here, where again, eventually, if you fix the noise and take time to infinity, you saturate at the best possible outcome, but the saturation is much slower. It's a power law, which again, you can predict. So I hope I've convinced you that systems with long-range memory are interesting. There's rich fluctuation behavior. And also these reinforcement effects can lead to interesting trapping effects, different classes of behavior, even in a very simple model. And if you have different utility distributions, you have to worry about how to escape the wrong trap. And it turns out that under certain conditions, there's an optimal level of noise, which maximizes the returns. Lots of extensions and further things to do, but let me stop there. So there's time for 1 or 2 questions.
Thank you very much to the speaker. Thank you, Rosemary. I think we have time for a quick question. Yeah, who want to make a question? Yeah, there is. Here is what the size if the fixed point will be symmetric or asymmetric for large T? Question mark, I guess.
Yeah, so I think I answered that in the talk. And so the crucial thing is that basically the tails of the utility distribution, and that gives you these different classes of behavior. I think the question came in before I explained that, so hopefully it's now clear. If not, do come back to me, Samida.
Thank you. So thank you, Rosemary, for the nice talk. And then I think we can go to the next speaker. Let's thank again. Thank you. And now we are going to the next talk. The speaker is Alexia Oufev, Institut Néel, France, and she is going to speak about 2-qubit engine fueled by entanglement and local measurements. Please.
Thanks for the introduction.
That you have 25 minutes plus 5 minutes for questions.
Yeah, thanks. So, yeah, thanks for the introduction, the invitation, even if I would obviously prefer to be physically present at this conference. So the name of the conference is Statistical Physics of Complex System, and I'm afraid to say that I'm just going to talk about 3 quantum systems, but at which level should we put complexity? This is an open question because they are quantum, these guys. So I hope it will still fit in the scope. So the results that I'm going to present, they're the result of a very nice collaboration with American colleagues, so Kater Murch and Andrew Jordan, respectively at St. Louis and now at Chapman University. And these are the young guys that participated actively to this work. The outline of my presentation is the following. So first, I will present you some new kind of engine that is quite different from the type of nano engine that you find in, I would say, mainstream stochastic thermodynamics, which are powered by quantum measurements. So in other words, it's enough to look at a quantum system to turn it into an engine. So I will explain you how it works and what are the fundamental insights behind this. Then I will present you the core of this talk, which is a 2-qubit engine. And I will use this 2-qubit engine to try to describe a little bit more deeply what I just briefly mentioned so far, which is the measurement fuel. So where does the energy provided by the measurement come from? And the fact that I will be able to describe fluxes of energy within entangled system will allow us to understand this better. So that's the menu. So first, so the whole talk and the whole proposal is based on this idea that quantum measurement can play a specific role in stochastic thermodynamics. So usually when you think about a measurement, you think of it in terms of information extraction. But the fact is that in quantum physics, measurement has another facet, which is the fact that it perturbs irreducibly a system. When you look at a system in quantum physics, you perturb it. And if you draw the consequences of this from the energetic point of view, quantum measurement can provide energy to a quantum system. So these are these measurement-induced quantum fluctuations I'm talking about. And this perturbation, it is also at the origin of specifically quantum stochastic trajectories, where the stochasticity of the trajectory doesn't come from the presence of any thermal mass. Only, again, the fact that I'm looking at the system generates randomness in the trajectory of a system. So the bottom line of this is that it's possible to build a perfectly consistent thermodynamic framework based on the randomness induced by quantum measurement only. No thermal mass in the picture. And this is the game that we have played a few years ago with my group and collaborators. Sorry, I want to change slide. Yeah. So what is this framework about? So as you can see here, the parties that are involved are extremely simple. I mean, this scenery, you could find it in a lecture for undergraduate on quantum mechanics. You have a quantum system that is, on the one hand, driven by some entity with a time-dependent Hamiltonian. And on the other hand, you measure your system projectively on discrete times. So you apply the measurement postulate. So this is Schrödinger, and this is the measurement postulate, to say it in a brute way. And with this, actually, you can build an essential quantum trajectory, because if you have your system that is in a pure initial state, and if you have access to all the measurement outcomes of your measuring device, then you can know, and obviously, as you're the controller, you also know the Hamiltonian that you apply. You can rebuild at any time in which state your system is. So this is a sketch of the typical quantum trajectory that you can build that way. Here, you have the Hamiltonian evolution. You know how to build this. And here, these are the stochastic quantum jumps. But you know here from which point to which point you jump, because you have access to the measurement outcomes here. So this is a stochastic quantum trajectory. And now we are in a thermodynamic talk. So starting from this, you need to define internal energy. And the internal energy, I'm simply defining it as the expectation value of my Hamiltonian along this trajectory. So very intuitive. Now, what is the first law in this transposition of standard stochastic thermodynamics. The first law, you need to define work and heat. So just like in stochastic thermodynamics, I'm going to define work as the energetic quantity that is exchanged during the continuous evolution. And it can be seen as the deterministic energy exchange with the controlling device, while heat, so I'm putting quotes here, this is because there is no thermal bath, quantum heat is exchanged during the quantum jumps that are induced by quantum measurement. So this is a stochastic energy exchange, which has no classical equivalent. They are really intrinsically due to measurement back action and to the fact that when you measure, you do something to your system in quantum physics. With this, the first law is guaranteed by construction. And you may expect the second law, but I won't talk about the second law here because I have no time for that. And the first law is well enough to what I want to present to you. Before I go further in the proposal, I want to take a simple example. My example is a qubit, so a two-level system which has two states, 0 and 1. And I'm going to do the simplest thermodynamic transformation I can think about, which is preparation and measurement. So I'm preparing my qubit in the ground state, and I'm measuring sigma x. So sigma x, the basis is a bit tilted, as you can see. There are two stochastic trajectories. Either I jump from 0 to plus, or I jump from 0 to minus. And the fact is that since I start from the ground state, each state I will end up into will have more energy, which means that measurement has provided energy to my qubit. So meet the quantum heat. Actually, this is the simplest example you can think about. And if you think about it from a mathematical point of view, it's obvious in the sense that I'm measuring an observable, which does not commute with the free Hamiltonian of my system. And since there is not this commutation, there is nothing that prevents me from having a change of mean energy of my system. So quantum heat is transferred on average during this step. And now I want to use this property to build a quantum engine. So just to give you the general strategy, this is the usual sketch that you have in mind when you think about an engine in classical thermodynamics, or I would say thermal-based thermodynamics. So you have thermal baths, so hot source, cold sources that induce thermal fluctuations. And from these thermal fluctuations, you can rectify them and possibly extract work from the protocol. What I want to do now is basically to replace the hot source that provides energy by a measuring device, and then extract work from quantum fluctuations. So this is actually the essence of what I called measurement powered engine. And so there have been a few since the first proposal we made in 2017. And always based on the same idea, you have a quantum system, you measure it projectively, you extract some work, that's magical. So the position of the work I want to present today after this long introduction is the following. So far, all the measurement-driven engine we had seen in the literature, they were based on the situation of a single quantum system undergoing a classical, a measurement by a classical device, which means that the measurement channel was not modeled at all. So in the work that I'm going to present you now, we have tried to answer two questions. The first one is, how can we extend this idea of measurement-powered engine to multipartite entangled working substances? So typically the two qubits that are in the title of my talk. And the second question is measurement energy, which I described you as heat so far, is it rather heat or work? Because you can also put yourself from the point of view of the guy who is measuring. And from this point of view, well, you spend work to do the measurement. So how can we understand this kind of double perspective on measurement, and can we get a unified point of view on this? So that's the kind of question we have tackled. which brings me to the second part of the talk, which is the principle of the 2-qubit engine. And the principle is very intuitive. You have 2 qubits, so a red and a blue, or this to say that the red qubit A has less energy than the blue qubit B. And at time 0, you excite the first qubit. So you put an excitation here. And then the 2 guys are coupled. So a long time, they get entangled such that the quantum of energy that is here, it basically gets delocalized between the red qubit and the blue qubit. And then you perform a measurement using a classical device for now. So you ask the qubit, say the blue qubit, you ask it if it is excited or not. And from this, there are 2 options. Either the blue qubit is not excited, which means the excitation is in the red qubit, and we are back to the initial state, basically. Or your measurement, and this happens with a finite probability, your measurement reveals that the excitation is in the blue qubit. And in that case, if you look at what happens on average, you gain energy because you have a finite probability to get the excitation in the qubit that has more energy. So how do we explain that? Actually, this is typically the same effect I described you before, in the sense that we can write down the Hamiltonian for the 2 qubits. There is a local term with the eigenenergy, the free energies of each qubit, and there is a coupling term which describes the exchange of the excitation between each qubit. And when I measure, I actually measure something that commutes with the local term. So the observable that I'm measuring does not commute with the total Hamiltonian of my 2 qubits. And because of this non-commutation property, I get this input of quantum heat. So we can do the energetic analysis of this from a classical point of view first. So actually, there are 2 conservation rules that really allow to grasp the essence of the mechanism. With this Hamiltonian, you have a first conservation, that is the conservation of the number of excitation. I start with a quantum, I end up with a quantum, there is no other option. And we also have, so because of this conservation of the number of excitation, I can look at the local Hamiltonian, and what I see is that it oscillates, which is normal, because if I start from the red qubit here, then I know that my excitation has a probability to go to the blue qubit, and if I strictly add up the 2 energy terms, my local energy increases. But then I also have the conservation of the total energy of the 2 qubits that involve also the coupling term. And actually the coupling term, it oscillates on the opposite sense to compensate for the increase of the local energy term. So this coupling term can really be seen as some sort of binding energy that is here to ensure both the conservation of excitation and the conservation of energy. So what happens when I do my measurement? When I do my measurement, actually, I'm erasing the coherences between the 2 states, or I'm erasing the entanglement, basically. I end up in a mixed state. Either my excitation is in the red qubit or in the blue qubit. Doing so, I just strongly increase immediately the binding energy. I erase it, it goes to 0. And therefore, the total term, the total energy of my 2 qubits, it increases by the same amount. So this is what I call here the measurement energy or the quantum heat. So we could use it, and that's what we have proposed in the paper. We could use it to build the Maxwell-Dimon engine just by playing with this entangling operation, the measurement, and using the information extracted by the measurement to feed back on one of the 2 qubits and extract the work. And finally, erasing the memory of the daemon. I won't present this part of the game because I want to keep time actually to open the black box and to analyze where the measurement energy comes from. Excuse me, my chairman because I didn't notice which time I started. How much time do I have yet left?
You still have 10 minutes.
10 minutes, perfect. So yeah, the final part of the talk is devoted to modeling the origin of the measurement fuel. So far, this measurement fuel, as I told you, I treated it like heat because it corresponds to energetic fluctuations that stem from instantaneous projective measurement. So from the 2-qubit system side, there is an input of energy that goes together with an input of entropy. But now I want to go beyond this and actually stop looking at the measurement only by using the measurement postulate, which does not allow me to model the measurement channel, but start providing a microscopic analysis of this measurement channel. And this is based on what in quantum physics we know as von Neumann pre-measurement model. So basically, we are going to model the measurement as an entanglement of the system with a quantum meter. And you see the sketch of this measurement, this pre-measurement here. So what we are going to do is to couple the 2-qubit, the blue qubit, to a quantum meter here that is another qubit that starts from a well-defined state. And we are going to entangle this blue qubit with the quantum meter to model the measurement. Okay, so in the ideal situation for this pre-measurement, the blue qubit and the red qubit, they are uncoupled. What happens is that, so we switch on the coupling between the blue qubit and the quantum meter. So the qubit meter coupling, it has this expression here, where you can see that, so we have a dynamic of the quantum meter that basically depends on the presence of an excitation in the blue qubit. So we can start from this state where the 2 qubits, they are entangled. We couple them to the meter prepared in some 0 state, which is the initial state. And then after some time, we build a tripartite entangled state or GHZ state where the quantum meter state depends on the state of the blue qubit, as you can see here. And this corresponds to a perfect non-destructive pre-measurement, okay? And the time at which this state appears, we are going to dub it TL. So now we are not in this situation in the proposal for the 2-qubit engine because A and B, the blue and the red qubits, they are coupled all the time. And that's where actually the magic comes from. So the evolution now of the 2 qubits and the quantum meter, we can describe it by using the perturbative approach, very simply, where at 0 order, the 2 qubits act as if they were not coupled. And at first order, we have a small term here that comes from the fact that actually the 2 qubits are coupled. And what we are going to do is to analyze the energy flow along this pre-measurement process. Our thermodynamic system is the qubit, the blue, the red qubit, and the quantum meter. And what happens is that between the beginning and the end of the measurement, the tripartite system is totally isolated. We are really describing a unitary transformation of these 3 guys with a time-independent Hamiltonian. And what happens at the initial and at the last time of the process is that I have an external agent that is going to switch on and off the measurement channel, which corresponds to actually the same work input. So we won't take this into account in the modeling. So here's what's happening. So here you remember what's happening if we have the classical measurement picture in mind, where the measurement is instantaneous. So we have a jump of energy that corresponds to this input of quantum heat. Now with the modeling with the quantum meter, we are going to be able to zoom on this measurement and to look at the energy flows within this small window here. So what we must keep in mind during this process is that the local Hamiltonian term is constant during the measurement because it's very fast at the scale of the Rabi oscillation. So during this step, I have few time now, so I'm going to accelerate. I'm aware of the fact that the time flies. So during this measurement, what happens is that I'm starting from a correlation term. Okay, sorry. What we saw before is that the coupling term between the two qubits, because of the measurement, gets erased. And this corresponds actually to the input of the measurement energy. Now, with this modeling, with the quantum meter, we can see that actually this term exactly corresponds to the buildup of correlations between the two qubits and the quantum meter. So the measurement energy, to jump to the conclusion, with this modeling, we see that it corresponds to the transfer of correlation from the two qubits to the qubit meter system. And what happens is, while the measurement channel is switched off, these terms remain constant, and the input of energy of the external operator is directly input into the correlation between the meter and the blue qubit. So the measurement energy also corresponds to a work that is provided by the agent to the global tripartite system. So to conclude, if it was unclear, is this measurement energy work on heat? So it's, as always in thermodynamics, it depends on the thermodynamic system that you consider. If you consider the total system of the two qubits and the meter, what you have to model the measurement is a reversible entropy preserving energy input, and that's work. While if you just consider the local system of the two qubits that you are measuring, then the measurement corresponds to some irreversible energy input that leads to some entropy increase that can be seen as heat. So now you could also try to go one step further and ask, but what is, if I have a very global vision of the world, the physical world I'm trying to describe, is there a most fundamental point of view, or has this question even a meaning? And here, after years of headaches, my answer right now to this question is that it really depends on your favorite interpretation of quantum mechanics and of the measurement postulate. If you think in terms of measurement as the creation of a massive entanglement by unitary transformation, which means that your brain is more or less plugged like in Everett's interpretation, then you naturally think as measurement as a reversible entropy preserving process. And for you, in that case, measurement energy will be fundamentally work. But if, on the other hand, you have von Neumann legacy in mind, and you are more or less Copenhagen plugged, then you have this idea that there is always a classical measurement that ends the measuring channel. And this classical measurement, which in this view is fundamental, you cannot avoid the cut, the Heisenberg cut, then measurement is irreversible. It's not entropy preserving. So the measurement energy, from this global point of view, becomes fundamentally heat, or very similar to heat. So here are the conclusions and outlook. So I've presented you a corpus of work where we play with this double meaning of the measurement in quantum physics. There is information extraction on the one hand, but there is also a back action on the other hand, and this back action provides energy. And this energetic imprint of the measurement postulate, you can see it from very different sides. From the system side, this looks like quantum heat, and this quantum heat can be converted into work in measurement-powered engine. If you look at it from the operator side, there is a work cost, and in that specific case, I presented you this work cost is here to erase quantum coherences and quantum correlations. And if you pick up a global point of view, then the nature as heat or work depends on your favorite interpretation. And I would say it's open problem and there is no meaning to fight on that. And one important point that opens on application is that this framework I have presented you, which basically leads you to rebuild thermodynamics on quantum measurement only, it's valid in the absence of thermal bath. And this is well adapted to analyze like the energetic cost of quantum technologies where the fluctuations are not necessarily induced by thermal sources of noise. And I will stop talking now.
Thank you very much.
I stop sharing.
We have space for some questions, please.
Hi, Alessia, I'm Andrea Gambassi. So my question is about what happens if instead of 2 qubits, you start considering a statistical system or a larger system? Is the machine going to work anyhow? I mean, maybe some of the concept can be put more on the statistical framework. Has this been done?
No, this is really, so what you have in mind is to extend the concept of measurement powered engines to systems that could be, for instance, massively entangled. Is that what you have in mind?
Yes. Some, for example, I mean, the simplest case could be a spin chain.
Yeah.
You have a spin chain, and then you ask exactly the same questions that you were asking. Because in the past, I studied something which, I mean, I didn't think about much whether to call it heat work. Eventually, I think I studied something similar after a quench and they called it work. Maybe I was too superficial, but so the idea could be to try to see, you know, this concept when your system is not a simple 2-qubit system, but is a chain.
Yeah,
okay.
that would be very interesting. I would say that to stick to the original concept, which is still exploiting the measurement back action as an energy source, what you need to keep is pure states, because you want the measurement back action.
Okay.
But apart from that, yeah, so you worked on that already. I mean, you pinpointed the measurement energy.
No, not really. Maybe I send you a message. We can discuss. Yes. Okay.
With pleasure.
Okay.
Thank you.
Okay. Are there other questions?
We have a question here.
Yeah.
Hi, Alexia. I'm Pedro from University of São Paulo. And in your 2-qubit engine, you have one step that you have to couple the qubits, and also you have one step that you have to measure. And if you do it really fast, then they don't have time to produce a lot of coherence. And also you can enter the Zeno effect regime because you are measuring too fast. And I would like to know if you looked at these two things, and also whether this is a limitation for physical applications and physical implementation of the engine.
If the Zeno effect would be a limitation, you mean?
Yeah, because if you build the engine, you can't go too fast. So I don't know if in the lab.
Because the Zeno effect, on the contrary, is a good thing. Because, okay, so maybe the Zeno effect is a good thing, but maybe the 2-qubit engine is not the best system to see it. So I'm going to do a fast answer, and maybe if you want, we can exchange more. But the fact is that the Zeno effect, it allows you to provide energy to your system, and at the same time not to have to pay the price that your measurement is stochastic, because you measure so fast that you basically freeze your system in a certain state. There is not any stochasticity anymore in the measurement. And if you build a Maxwell daemon, for instance, then you don't have to erase the memory anymore. So you can switch to a regular Maxwell daemon engine to basically a transducer of quantum heat to work without passing by the step where you need to process information. These are engines that work without informations, basically. But we have studied this in the 2-qubit engine, and also in the first proposal of measurement-powered engine in 2017. That was actually the magic.
Okay, thank you.
Hi, Alessia. This is Gonzalo Manzano. I'm also very interested in the properties of these energetic fluctuations due to the measurement back action. And so I was thinking whether these energy fluctuations are also similar to kind of stochastic sources of work, like for instance in electric currents or kind of stochastic forces that or non-conservative forces apply to particles and so on. So because to me, this just remembers me also kind of this kind of sources in which even if you have they are stochastic, but the energy that they exchange is more similar to work. This is also, for instance, the case for thermal baths at infinite temperature, right? In which you stochasticity, nevertheless, but they are considered to be like work because they don't contribute to the entropy production.
Yeah, so the debate of on heat and work, and this is also an answer to the first member of the audience who asked me the question. The more it goes and the more artificial I think it is. So I insisted a bit on that just to put efforts to try to close the debate, because actually it depends on the point of view. It also depends on your interpretation. It depends on your background, what you think of the measurement postulate. It depends on what you allow to call heat or not, because I know some experts in the community who wouldn't want to dub something heat if there is no thermal bath around. So I think at the end of the day, you need to be consistent and also involve more experimenters in the game. And fortunately, they are more and more present to do experiments. So now regarding the stochastic work source, I must confess my ignorance. I don't exactly know what you have in mind, so I can't make an accurate answer or any interesting comment. I'm interested in knowing more. Sorry, I can't be more precise.
So let's thank again Alexia for the very interesting talk.
Thank you.
And we can move to the next speaker of this last speaker of this morning session is Hugo Touchet, Stellenbosch University in South Africa. Hi, Hugo. How are you?
Hi, ciao.
And he is going to speak about machine learning of large deviations.
Thank you, Roberto. I assume that you see the slides and you can hear me.
Yes, we do.
Yes, thank you. Thank you for the organizers for organizing this conference and then making concessions to have online presentations. Of course, we would like to be there in person, and then hopefully we'll be able to do this next year. For now, I'll give the presentation online from South Africa. I want to present some work that I've done recently with Yeve Jan and Grant Bruskoff from Stanford on combining some tools from machine learning to estimate large deviation functions. So this is the reference there, which I'll be describing. It's been submitted recently. I'll start with the context. So we consider a Markov process, which is meant to represent a non-equilibrium system driven in a steady state. So it could be one particle, one Brownian particle, or it could be a system of interacting particles, but it's driven out of equilibrium by external forces or reservoirs in a steady state. The cartoon picture that I'll be using for the presentation is the following. So we can simulate or observe trajectories of the system like this, trajectory x of t over time. And so what we do is that we monitor the system over some time interval 0 capital T. And then as we do this, we measure some observable. So we track some observable, which I'm going to call AT. So the observable itself is a function of the whole trajectory. It could be something like the integrated work that is done by the system, by the external force on the system. It could be an integrated current. It could be the entropy production. Usually these quantities are time integrated, and they relate to currents, or they relate to the state of the system itself. So this is up to the model or the system that you're interested in. What we're interested in is to calculate the probability distribution of the observable in the long time limit. And then we know in many cases that that distribution has a large deviation form, meaning that when capital T, so the observation time, goes to infinity, that distribution peaks exponentially around some value, which is a typical value of the observable, which is at the same time as the expectation of the observable. But the main point here is that you have this exponential concentration, which is described by what we call a large deviation principle or a large deviation approximation. So that funny sign here just means asymptotically, when time goes to infinity, this is the dominant scaling of the distribution. And once you know this, then what you're interested to calculate is the exponent of that scaling, which we call the rate function. And so that's this part here in red. So that rate function will basically give you all the information that you want to have about the distribution. It characterizes the distribution to the dominant time scale for the observation time. Often, so we want to calculate that rate function. This is not an easy problem. And then often what we do is that we look at the generating function instead. So we take the expectation of the exponential of time, some parameter, real parameter that we call lambda, and then we have the observable. So this is a generating function. This is a Laplace transform. And if you know that the distribution scales exponentially, the generating function also scales exponentially with time, with some exponent that we call the scale cumulative generating function. So it's a cumulative function because you would take the log of the expectation to extract that function. So whether you can calculate this, if you can calculate that function psi of lambda, then I'll show this in a later slide, by Legendre transform, you can get the rate function. And again, we're after the rate function. So these two functions, the rate function or the scale cumulative generating functions, will give you the likelihood of fluctuations for the observable. What we're also interested is to what I call the prediction problem, which is try to understand how fluctuations arise in time. So this is the cartoon picture. I'm interested in this type of fluctuation here in the tail. It's got low probability, so it's obviously a fluctuation. It's not something that I can observe many times if I monitor the system. What I want to do is track down all the trajectories that led to that value of the observable. So here I'm doing this by just coloring those trajectories. And what we want to understand is whether those trajectories can be described as a stochastic process on its own, and this is what we call the fluctuation process. Mathematically, this corresponds to conditioning. You want to take all the trajectories and then condition those trajectories on seeing a particular value of the observable. So it's a conditioning in terms of stochastic process, and then you can show that that conditioning is also a stochastic process. In the long time limit, it's a Markov process, and then you can write down what that Markov process is, and I'll refer to this as the fluctuation process. Okay, so this is the overall context. We're after calculating the distribution of some observable for a non-equilibrium systems. Now, how do we get this? So as I mentioned before, the rate function can be obtained as the Legendre transform of that function psi of lambda. So the focus of the talk will be on that function psi of lambda. For a Markov process, what's interesting is that that function, the scale cumulative generating function, is actually the dominant eigenvalue of some linear operator that we call the tilted generator or the tilted operator. So essentially calculating a rate function for a Markov process boils down to a spectral problem. You want to calculate the dominant, you want to solve a spectral problem to extract the dominant eigenvalue as a function of that parameter lambda, and then you'll get this function, and by the Legendre transform, you get the rate function. Moreover, when you solve this spectral problem, you get the fluctuation process, which I've just described. In the case of a diffusion, for instance, the fluctuation process is a diffusion in which the drift is modified by the gradient of the log of the eigenfunction. So the scale cumulative generating function will be the dominant eigenvalue, if you select the eigenfunction related to this dominant eigenvalue, then with this eigenfunction, you can compute a modified drift, which we see here, which will give you the modified drift of the fluctuation process describing those red trajectories that I have here. So those red trajectories give rise to the fluctuation here. So in a sense, that fluctuation process is a modified process. It's an effective process that has those values of the observable as a typical value. So it describes how those fluctuations are described. And the little lambda parameter that you have there is a Lagrange parameter. It's like a temperature. You fix it by the derivative of the rate function. So this is what we call the duality. This comes from the Legendre transform. So lambda is like an inverse temperature. If you want a large fluctuation, you change that lambda to reach that value according to the derivative of the rate function. Okay, so this is something that's been known for quite some time. We have that effective process that creates or explains how the fluctuation is created. And at the same time, this is good for simulation. It's a good process for simulations because it makes a fluctuation typical. This is how you change the drift essentially to make the fluctuation typical. And then it describes how that fluctuation happens with that modified drift. So this is a process that is useful for simulation, but the problem is that we need to solve the large deviation problem to get that fluctuation process. So there's no free lunch here, whether you solve the spectral problem or whether you know the fluctuation process, then it's the same thing. Okay, so we want to calculate the rate function. We want to calculate we want to construct the fluctuation process, and there are many methods that you can use to do this. There are only a few systems that you can treat analytically, so many numerical methods have been developed over the years to solve that problem. Not actually specifically sometimes for the large deviation problem, but for rare event simulations. But once you have methods for a rare event simulation, you can apply those specifically to the large deviation problem. So here I'm putting a kind of landscape of the different methods. I'm not going to go over all of this, but you have different families. So you have sampling methods like importance sampling, you have splitting or cloning, then you can tackle the spectral problem numerically directly. So this is a first approach. You might want to solve the spectral problem numerically, and at the same time we know that there's an optimization representations of these functions, or so you can try to solve that optimization or control problem, which I'm going to describe actually in the next slide. The problem with this is that often beside actually solving a spectral problem, which is not easy to solve, often, especially if you deal with many particle system, you have to represent functions like the eigenfunctions in a very high dimensional space. So that's the bottleneck here. For the sampling or the cloning, the problem is that you have to simulate many trajectories, many clones, and this is memory time intensive. So there are different methods available. Some are more adapted to some problems than others, but they share they share different difficulties, but it boils down to solving a difficult problem. And again, there's no free lunch. If you can solve the problem using cloning, it means that you've solved the spectral problem or an optimization problem. On the other hand, if you solve that spectral problem, you could use the solution to actually do cloning and importance sampling. So they're all related. The approach that I'll present is actually based on a optimization representation of the large deviation function, which was developed in the 70s and 80s, and then I've worked with this with Raphael Chetrit more recently, and then Rob Jacht and Peter Solik also worked on this at the same time. So the idea here is based on importance sampling. So this is the original process, and the original process will generate some measure probability for the different trajectories, and what you do is that you want to change that process to generate a new distribution of trajectories. So think of the blue trajectories as being the typical trajectories of your system that gives rise to typical values of the observable, and we want to change the process. We want to bias the process or tilt the process in the direction of a fluctuation. So to do this, you modify the process, meaning you modify the distribution of the trajectories. And then the control representation or the optimization representation says that the scale generating functions or the rate functions will actually be minimizers of some cost function. And the cost function is quite interesting. The cost function is a kind of log of the ratio of the two path distributions that you generate from the original process in blue to the modified process in red. So if you have the ratio of that path distribution, that gives you a random variable, which is the cost. That's the random cost associated with a given trajectory. If you take the expectation, this is the relative entropy between the modified process in red and the blue process, the original process in blue. So that's kind of control cost. It's additive in time, you can show this. And so if you minimize this in the long time limit, like this, then you get the scale generating function. You see you have the lambda parameter there. If you constrain the minimization, if you minimize the cost subject to reaching a given fluctuation, you get the rate function. So in a sense, what we've done here is to represent the large deviation functions that are the rate function and the scale generating function as an optimization problem. On this side, you have an unconstrained minimization problem. On this side, for the rate function, you have a constraint minimization problem, and they are related by Lagrange multipliers, and this is the same as the Legendre transform that connects the rate function to the scale generating function. Now, we know what the minimizer is. We know what the optimal change of process is. That's the effective process. That's the fluctuation process I mentioned before. And so you can view now the fluctuation process as being a control process. You modify the process in the control way, and it's optimal in the sense that it's the one that minimizes the cost to give you the large deviation functions. So this is one way to represent the whole of large deviation theory and the fluctuation process as a control problem. Now, for the purpose of simulation, I'm just going to mention this. We can measure the cost, we can calculate the cost over a trajectory, and the cost for diffusion is just a distance squared between the original drift of the diffusion minus the modified drift. So this is interesting because now we have a quadratic cost, which is simpler to deal with for diffusion. You can also define a cost for jump processes or Markov chains. It's just slightly more complicated, but we know these formulas, so we have the explicit expression for the cost. Okay, so now I'm going to describe some previous approaches that have been followed to solve this problem. Now, again, we have two approaches. Either we solve a spectral problem, or we solve an optimization problem or a control problem. It's the same. So and these are related. Again, there's no free lunch. If you know the solution to the control problem, it means that you know the spectral problem and vice versa. The big difficulty here is to represent the eigenfunction. So a natural approach is that you want to approximate the eigenfunction into some basis of function. So you want to approximate this using some function u that has a bunch of parameters. And so this is the architecture that you're going to use to approximate that eigenfunction. So there are many possible choices, and so in the past people have used basis functions like Fourier transform, Fourier basis to represent the eigenfunction, or Lagrange polynomials, or Legendre polynomials, and different things. And then a lot of work has been done on this by David Limmer's group at Berkeley. I'm putting some references here. For some other systems, especially jump processes, defined on nets or interacting particle system, you can also use matrix product systems or tensor nets to represent the eigenfunction. So this is a different representation of the approximation for the eigenfunction. It's a different architecture that will involve different parameters. Then more recently, it's quite natural to use neural networks because you want to represent a very high dimensional function. So it just makes sense to use neural networks to do this. It's been done in many contexts, and now people are starting using the tools that people have developed, for instance, in machine vision to represent eigenfunctions. So I'm putting some references on this. And then once you know that you can represent these functions as a control problem, it makes sense also to use ideas for reinforcement learning to try to solve the control process. And this has been done very recently by the group of Juan Garan in Nottingham. And more recently, actually, the two groups have started working together on this idea of using reinforcement learning. The approach I'm going to describe, and this is the approach that we followed in the paper that I've mentioned before, is slightly more direct. What we're going to do is that we're going to do a gradient minimization of the cost function related to the control problem. So we take the control problem as the line of attack, and then we try to minimize the cost function directly by simulating trajectories. So there's no reinforcement learning. We just do a gradient minimization of the cost. And then the input here is that we're going to use neural network to represent the control force. So there's going to be a minimization of the cost function and a feedback now to represent the control force, and it's all based on neural networks. So I'm going to describe this now. So this is what I call a stochastic minimization. Again, we have the cost function, which I've mentioned before, and what we want to do is to minimize the cost function in an unconstrained way. So I'm going to solve this problem. I want to minimize the expectation of lambda, the observable, minus the cost function, and this is the cost estimator which I'm using for the cost function. And I do this in the long time limit. So what we do is that first we initialize the neural network to represent the force. So initially we don't know anything about the control force, the optimal control force. So we just initialize the parameters in some random way, or we just initialize the parameters in such a way that we represent the initial drift. And what we do is to simulate M trajectories. So we simulate an ensemble of trajectories, which we call batches. That follows the terminology used in machine learning. So I'm simulating M short time trajectories. So we'll deal with the long time limit later, but essentially I just need some ensemble to calculate some kind of mean cost. I need many trajectories because if you calculate the cost only over one trajectory, then the gradient is too noisy. So you need M trajectories just to make the expectation or the average more well-behaved. So you compute the cost for those M trajectories as a mean over the M trajectories, and this is calculated also over the observation time t. Then you compute the gradient because you want to update the neural network, and then you do this by normal gradient techniques for neural network. So you can do this by standard backpropagation, and then we'll see some example of this in a minute. So you can use just off-the-shelf software to do backpropagation to calculate the gradient, or if the system is quite big, and then we'll see an example of this too, if the system has many particles, then backpropagation is not really efficient, the complexity is too high. In that case, you can use an adjoint method to compute the gradient, which is very efficient because it only uses the trajectories that you've simulated. Once you have the gradient, you can update the neural network. So now the parameters will be updated according to the normal stochastic gradient formula. And then gamma will be the learning rate, which is an hyperparameter for the system. Now, simulating these M trajectories and computing the gradient is one step of the training. So you repeat the step 1 to 4 many times. So you repeat just the training steps. So I'm simulating M trajectories, I update the network, I'm simulating another M, I'm updating the network, and so on, until you see convergence of the cost function. So this follows normal training methods for neural network. And then once you've reached convergence, then you have one point. So you have the scale current generating function for one particular lambda. So then what you do, of course, is that you repeat this for different lambdas to construct the large deviation function. And from this, you can use the Legendre transform to get the rate function. There's some extra steps that you can put into this. For instance, instead of starting with some fixed lambda, you can start with a lambda that's close to 0. And then you can just step the lambdas gradually. So then you can use the final information that you have for a small lambda as the initial condition for the next step for the other lambda. And then with this, you can cover a whole window of lambda values using, again, as initial condition, the last convergence point. And this is called, in machine learning, transfer learning, because you're just using the learn network to inform another simulation for different parameters. And that usually speeds up the convergence quite. Also, if you're dealing with dynamical phase transition, you can use replica exchange. So you're simulating two systems for different lambdas, and then you swap them consistently, and that also accelerates the convergence. So this is the algorithm. It's based on the neural network. I'm not putting the details of the neural network that we're using. It's just even off-the-shelf software for representing that function. You just have to specify the number of layers, the number of nodes per layers, and then it's basically, you just press play and that goes into this. You just have to be careful to track convergence to make sure that you're going somewhere. So I'm going to present now two examples, one simple and then one more involved with active Brownian particle. I'll start with the simple diffusion. This is just a test to see whether the algorithm works well in the low noise limit. This is a system that was studied in 2016 by Nemoto, also Freddy Boucher. So this is a simple stochastic differential equation. You see it here. It's a one-dimensional system with a quartic potential. So it gives rise to this X3 diffusion drift. And then the observable that we're tracking is this one here. So the reason for choosing this one is that it's not a linear observable. It's not quite quadratic. It's a mix of the two. And this is non-trivial because it's a quartic model. So it doesn't have an exact solution. It has one for the low noise limit, but otherwise it's not just the trivial Einsteinian limit process. So for this, we did the simulation. So we have here, it's very simple. We're using 2 layers for the neural network, and we have 50 nodes per layers. For the training step, we just simulate 200 trajectories, more or less, for a small time t, which is just t equals 10. So here, actually, we can calculate the limiting function, which normally mathematically arises in the long time limit by taking small time. And then you can track down convergence by looking at time. But what we've seen, and then it's also something that I knew from previous simulations with other techniques, is that you don't have to go to long time to get the large deviation limit. For this system, we use direct backpropagation. So there's no fancy algorithm for calculating the gradient, and you have the results here. So we have very smooth results for the scale-clone generating function, and then we can decrease the epsilon, which is the noise amplitude, to get to the non-analytical result, which is the solid curve here. What's interesting for this system is that there's a dynamical phase transition, so there's a non-analytic point at lambda equals 0. You see the second derivative here, it jumps, so there's a second order phase transition here. Here I'm showing the training convergence of the scale-clone generating function for different lambdas. So you see we just initializing the network kind of random, and then we just following the training steps, and then we see convergence of the scale-clone generating function. You can also plot the cost function, and then it converges with these plateaus. There's a kind of shift here which is related to the network itself. There's some dynamics, but that's a dynamics of the neural network, because here this is the training step. I'm not going to discuss the dynamical phase transition so much. I just want to really focus on the numerical algorithm as such. And so here you have the result. One good thing about the algorithm is that there's no slowing down as you take smaller and smaller noise. The algorithm is just the same. You don't change the number, the simulation parameters that you're using, and then the quality of the results is just the same as epsilon goes to 0, which is not the case for cloning. Cloning has this problem that you have a critical slowing down of the simulation when epsilon goes to 0, so you have to increase the population size as you decrease the noise, and there's no such problem here. For the second application, I'll just describe something more physical. This is something we've seen yesterday in some of the talks. This is a system of n interacting Brownian particles that are driven by a potential, which I'll take here to be a Weeks-Chandler-Anderson potential, so WCA potential, which is a bit like a Leonard-Jones potential. And then they're driven by some angled diffusive alignment, which makes them active. So you have a bunch of active Brownian particles. This is the set of stochastic diffusion equations that are coupled, and they're coupled with the potential, but also with the angles. So that alignment angle is driven by an angle phi, which is diffusive. So the angle actually follows a Brownian motion itself, and that aligns the particle in some direction with some velocity v there. So that's the system. You have now n interacting particles. The control force now is a control force for all the particles. So it's quite a high dimensional object. And so this is why now it makes sense to represent this with a neural network. The observables that we're tracking is the entropy production. This is known to be a nice observable to track because it shows also a dynamical phase transition, which is related to particle bunching and collective behavior of the particles in a fluctuation sense. And so that's been described also yesterday in some of the talks. So here I'm showing the results for 40 particles, 80 particles, and 200 particles. This is now the derivative of the scale clear generating function, we know that the derivative of the scale clear generating function psi of lambda gives you the typical value of the entropy production for that lambda. So it gives you the fluctuation value by tweaking the inverse parameter lambda here. So these are the curves, and then by the Legendre transform, we can calculate the rate function, which I show here with the minus sign, so it's actually upside down. So we have the typical behavior here, and then we have the rate functions for the different particle size. So the one I want to focus on is this one here. So you see that you have different likelihood of the entropy production, and with that we can relate to different configurations. So the very unlikely fluctuations of the entropy productions are related to particle bunching. So you see this is a snapshot of one trajectory of the whole system. And then here you have just the normal motion that you would see if you don't bias the system. So that's the typical behavior of the particle, which has no bunching. So again, I'm not going to discuss any of the physics of this. This will be the subject of another talk. I just want to show how the algorithm is working here. One thing I should mention is that for this particular system, we do the gradient calculation, the gradient training for the neural network, but we don't use standard backpropagation for this, for calculating the gradient, because the system is too big. If you have 40, 80, or 200 particles, when you do the backpropagation, the size of the backpropagation actually increases with the number of layers that you have in the neural network, and it just explodes. So in order to calculate the gradient here, we use this other method that I've mentioned, the adjoint method. And the adjoint method has no complexity whatsoever, because all you need to know is the trajectory that you simulate, and then the inverse, the time reverse trajectory that you've simulated. So you only need to keep and store one trajectory at a time, or in this case, the M batches. So it's very low complexity. That's about it. So I'll go to the conclusion. So what I've discussed has some advantages over the other methods that have been devised so far. One is that it's low complexity. So we have the code available, and then you can see most of the code is actually built from off-the-shelf packages that you can use for neural network, especially if you're only using standard backpropagation and not the adjoint method. So it's low complexity. You're not reinventing the rules here. You can use PyTorch and other packages in order to build a neural network. And then specific to your system, there's a PyTorch for stochastic differential equation, which is Torch SDE. It's got low complexity also because you don't need to store many trajectories like the cloning methods. You only need, as I mentioned, to store only one trajectory as you simulate, and then you can just erase a trajectory and then simulate another one. I focus mostly on stochastic differential equations, but you can apply this to Markov chains and jump processes more or less without changes. So it's very easy to code. It's kind of black box. You only need to tweak some parameters, but it's off the shelf and blank box, and it works the same whether you consider a discrete system or a continuous system, which is another advantage, for instance, over matrix product states, because these works only for discrete systems. Now, there are various questions that you can ask yourself and various problems that you have to deal with. So it's not all rosy here. One, which is common to all the methods, and in fact, it's a problem that you have to deal with whenever you're using neural network, is whether you reach the true global minimum, whether you've calculated the optimal control force and not just something that is suboptimal. So we're working on this now. Specifically for the large deviation problem, you can devise some tests to tell you whether you're in the global minimum regime. So for instance, if I go to the training here diagram where you see convergence, the fact that you see convergence doesn't mean that you converge to the global minimum. So that's a common optimization problem that you have to deal with. So we're working on this, trying to devise some tests to really make sure that you reach the global minimum. And then another more obvious problem is to look at the physics of the learned control force. So for the active run-in particle system, especially, my collaborators are looking at kind of characterizing the learned control force, which is the optimal control force that will generate fluctuations, trying to see if that force is local in any way, if it changes only the interacting potential, or whether it changes also the active part of the drift there. And another problem of concern is to apply this to many particles. So I've shown now simulations for 200 particles. the idea is to try to apply this to many particles, and this seems to be possible, and it seems possible to reach 1,000 or even more particles because the method is low complexity again. All you need to store always is one trajectory as you go along. So with this, I'll conclude. This is the reference again. If you want the details, there's also supplementary material about all the numerical details for the neural network. And if you're interested in the code, this is the GitHub address for the code that was devised mostly by Yabe, the postdoc working on this. If you want more information about large deviation theory itself, then I can direct you to my website. Thank you.
I think we're a bit in some delay, so there is space for a short question. Other questions, please?
Hello, my name is Pedro from São Paulo, and I would like to know if you see any clues, for example, in the stochastic differential equation that tells you, oh, now I need to use cloning algorithm, or now I need to use this machine learning algorithm. And to what extent did you compare this new algorithm to previous ones?
Okay, so there's not that many comparison, and it's something that we have to work on. So one point of comparison actually was this one, the first simple diffusion. So this system has been studied using cloning, so we can compare it. The advantage of the method we have is just that we're not simulating many clones. And again, as I mentioned, there's no slowing down with the noise parameter. So there seems to be some advantage here. Now, then for the first question, how can you decide for using one method over another? This is a very difficult question. I don't think there's a clear-cut answer here. It's also it's the same question that would you ask yourself if you want to solve a spectral problem or an optimization problem. There's not one method that will be the best. It depends a lot on the system that you study and the dimension of the optimization problem that you want to solve, and the particular nature also of the optimization problem, whether it's a discrete optimization problem or a continuous optimization problem. So I think what's going to happen in the future is that we're going to have this ecology of different methods that we can combine, and then we can use in different contexts. You can combine cloning with this method. You can combine importance sampling with this method, and so yeah, and then there would be some advantages in keeping all these methods and combining them.
Okay, thank you very much.
So let's thank Ugo again for the talk, and now we can go for the coffee break, and we reconvene at 11:10, so 10 past 11. So we will also for the participants online. So hi Ugo.
Ciao.
Thank you very much. Ciao. So, welcome back. It is our greatest pleasure to have Udo Seifert with us giving a talk physically in presence, a present talk. Thank you very much for the coming, I mean, in spite of the difficulties. And well, Udo doesn't need much of introduction. So please, Udo, you have 25 minutes for 5 minutes question. Thank you.
Andrea, thank you very much for the invitation. Also, thanks to Sebastian, Edgar, and Matteo for arranging this in difficult times. It's really appreciated, and it's my first trip since the pandemic. So I'd like to introduce you and to highlight a few aspects around this notion of this thermodynamic uncertainty relation. And I hope to convince you that it's arguably one of the most exciting developments which came out of stochastic thermodynamics. So we'll start with recalling the principles of stochastic thermodynamics using molecular motors as a paradigm, and then I'll come to the core topic. So the basic idea, so this is supposed to move. Where is the problem? Moving, okay. Good. So the basic idea is shown on this slide. As I guess most by now of you know, the idea of stochastic thermodynamics is to try to check whether and how the rules which have been developed 200 years ago to understand machines like this one, whether and how these rules can be applied to these much smaller machines on the nanoscale, like this rotary motor, the F180 PAs. Okay. Basic modeling concept is Markovian dynamics in this field, and I'd like to illustrate it using a real life experiment by Matthias Reeves' group. So they were looking at a small peptide, a small protein, which can fold in different conformations, and they've been able to distinguish 6 different mesostates of that molecule. The corresponding network is shown up here. And by applying a pretension to this molecule and just looking at time traces, they saw these clearly distinguishable 6 states, and they were able to measure the transition rates in this network experimentally as a function of the applied force. So for any given force, it's an equilibrium problem. And I like to use this as a, in my opinion, marvelous illustration of Markovian dynamics. So once we know we have Markovian dynamics, the concept of the mesostates arises on this time scale. So we're assuming that the very many microstates contributing to one mesostate, fluctuations of water molecules or side chains, that these transitions are fast. And then on the meso level, the capital IJ level, we have this Markov description. And the key point is that, as I have just shown you, the rates can be measured experimentally from such time traces, but the ratio of these rates then also defines the free energy difference of any 2 of these mesostates. And by doing this at a different temperature, you can also experimentally get the internal energy and the intrinsic entropy of each of these states. So my main point here is that these quantities are operationally accessible in such experiments. Okay, so there is a second paradigm for the dynamics, which is Langevin dynamics. And I guess most of you know by now that this Langevin dynamics in the overdamped case can be easily be endowed with a thermodynamic interpretation. Concepts like work, internal energy, and dissipated heat can be derived or can be applied to such a dynamics. And then, for instance, the total entropy production is defined pathways or trajectory-wise, essentially as the log ratio between observing the probability for observing a trajectory compared to observing its time-reversed x-tilde trajectory. And that turns out to be to have 2 contributions. One is the heat, and the other one is this kind of stochastic entropy. And then it's easy to derive exact relations like this integral fluctuation theorem or the detailed one up here. Many of you have seen this slide, but I want to make one point. If you now measure experimentally this distribution, which we did some 10 years ago with Clemens Bechinger in Stuttgart, and you plot the data in this logarithmic fashion, you get a slope. You get a slope 1, which is the fluctuation theorem. What did you learn? Not a terrible lot. You just learned that your experimental system complies with this Langevin equation. So the interesting part is, or the interesting aspects are systems where it doesn't work so easily. And a nice example for that is this rotary F1 ATPAs. These are data from a Japanese group, also 10 years ago. They are looking at the distribution of the angle of this rotary motion, which is made visible by looking at a micron-sized probe particle attached to the nano-sized molecular motor. Here you see traces of this angle as a function of time. One can clearly observe 120-degree steps. Now, if you plot the angle again in this logarithmic fashion, and if you assume that this dynamics was given by the simple rotary Brownian motion, you would predict that, again, there is a slope, and the slope should be independent of time. And that would be the fluctuation theorem for the simple dynamics. However, it turned out in experiments that the slope depends on the time over which you allocate the data, which tells you that this angle is not really equivalent to entropy production. So there is a hidden degree of freedom, which you do not see, which distorts the simple relationship. And in order to see that, let me recall one model which we developed for this system. So first, you can map this rotary motion to a linear motion, and then you have to appreciate that the nano-sized motor will jump in 120-degree steps, but inevitably there is some elastic linker between this probe particle and the motor. So when the motor jumps 120 degrees, essentially that spring is loaded, and then that particle may follow, or it may even pull back the motor. Of course, modeling this will then require thermodynamic consistency. So again, the ratio of the motor jumps has to involve the corresponding free energy difference. When you do that, you indeed get data which are quite close to the experimental one. So this is experimental, this is our theory, and you can measure the slope or calculate the slope as a function of time, and you find precisely what has been seen in the experiment. So my point in this introduction is that first, there are exact theorems like the fluctuation theorem, which are identities. And if you look at these identities in a certain system, they are either obeyed or they are violated. If they are violated, you basically know that you have not covered the relevant degrees of freedom. If you want to cover them, you can come up with specific models as we did in this case. But this will require a model. And it would be nice to have relations that are universally valid, and using those, you want to extract properties of systems in a model-independent way. And that's actually what the thermodynamic uncertainty relation achieves, as I'll show you now. But I want to motivate it with my motivation when I started thinking about it some 6 years ago, I guess. I asked myself a very simple question. Suppose you have a clock or a watch, and you have this watch in a finite time, finite temperature environment. So clearly there will be fluctuation. Clearly such a watch, such a clock will not be infinitely precise. And then the question is there a relation between the energy required to drive the watch, i.e. the battery, and the precision, i.e. is a more precise clock more costly in its operation? Not in its initial manufacturing, but in its permanent operation. And I'll give you the answer. Yes, there is such a relation. And what we know by now is that if you operate a clock at room temperature and you want it to be precise with, let's say, an error or precision of 1 second per day, you have to pay at least 10 to the minus 11 joule per day. Now, this figure sounds completely crazy, and it's not obvious at all. Perhaps not completely crazy, but certainly not obvious. And I'll now show you how you get to such a result and how universal it is. Okay. So again, you start, of course, with the simplest model. So my model for a clock is just an asymmetric random walk. So each step of, let's say, the second hand of such a watch is will require some process, some energy, for instance, ATP hydrolysis. So the simple clock is just the asymmetric random walk. And you know that after 1 minute, on average, this will have made 60 steps. But it comes with a variance, and this variance is given by the sum of the rates. So the uncertainty, the precision, is defined as the variance divided by the output squared, and that leads to this combination of diffusion coefficient and current J. Now the cost, we know the rules for such processes. So the ratio between forward and backward rate is the log ratio is given by the entropy production, and the entropy production is the change in delta mu of this chemical step. Now you combine these relations and you find that the product between cost and uncertainty is given by this hyperbolic function, and that is larger than 2 kBt. That's a trivial calculation. You just have to combine these two results here. Now, I wouldn't be talking about this if this was true only for this asymmetric random walk. But it turned out, and this is work with Andre, we looked at many networks, we did analytical case studies, we worked hard, but we were not able to deliver the proof, which was then given a year later by the MIT group. The result is that this relation between cost and uncertainty is true for any process modeled as a stationary Markov process at finite temperature. And now if you want, for instance, a precision of 1%, you have to pay at least 20,000 kBt. And from this, you get this number I quoted for the watch. So in a sense, slightly more generally, you can show that for any current, which is basically given by the sum over all links, and you can associate with each link ij, you can associate a time asymmetric weight d. For any such current, the variance, the mean, so the variance is embodied in this fluctuation theorem of in this diffusion constant, sorry, that is constrained by the entropy production, or turning the other way around. The stationary entropy production is larger than the mean squared divided by the variance. So you see, if you want a current with a very small variance, you have to pay a lot for driving the system. And I want to show you, because this is mostly a theory audience, I want to show you the kind of simplest proof. This was not the original one. This is now based on work by Dechant and SISSA. So they were looking at the generating function for general observable Q, which is defined as in Hugo Stuchet's talk this morning, as a functional of the trajectory. And now the idea is to bound this generating function through an auxiliary process with on the same network but different rates k dagger. So this is an identity, and then you use essentially Jensen, and then you find that this generating function can be bounded by this expression, which involves the Kullback-Leibler distance between the two distributions. P is the original one, P dagger is this auxiliary one. And now you have to choose this auxiliary one in a smart way. So you perturb the original one slightly through this parameter z. Then you get this cancellation of linear terms. And for the quadratic ones, you have this relation. And then by a variational ansatz, making sure that the new distribution is the same as the old one, you get actually this relation here for the variance of any such observable, or in particular, if such an observable is a current, you get this relation. And this now holds even in finite time t. The original was in the T to infinity limit, but we knew, and again, this was separately proven by Horowitz and Gingrich, that even in finite time, there is this relation. Okay, so now we have this, what can we do with it? Let me show you one example, which is on molecular motors, which I find particularly revealing about the power of this relation. So we're using here data 20 years ago from Bloch's group, where they were looking at the motion of a kinesin molecule against a specified force, which was realized by this kind of feedback trap, laser trap. And then they were measuring the velocity, which corresponds to the mean current. They were measuring the dispersion of this velocity, which I'll call diffusion constant, corresponding to this current. And typically that's experimentally quoted in this ratio called the randomness. So here you see data. This is the randomness as a function of the ATP concentration, which drives the motor. Or you can look at the randomness as a function of the external load for fixed ATP concentration. And these are data which have been around 20 years. Now we apply our uncertainty relation to these data. And how do we do this? Well, we look at the efficiency. Efficiency is output divided by input. Output is the mechanical work. So that's the velocity against the externally imposed force. Input is not known because you do not know how many ATP molecules the motor needs without making a model, and we don't want to make a model. But we know that the difference between input and output, that's what's lost. So we can replace the unknown input by the output plus the entropy production. And for the entropy production, we have this inequality through the velocity and the dispersion. So you see now on the right-hand side, they're only experimentally known or measurable quantities. On the left-hand side, there is thermodynamic efficiency. These are the data I've just shown you, but now I'm overlaying this bound in this colored curves. So for instance, let's take this point here. So this is the 45% line. So the statement now is that at this load, this molecular motor is at most 45% efficient in translating chemical energy into mechanical motion. And this is a model-free statement. I'm not saying that the motor is 45% efficient. I'm saying it is not more efficient than 45. It could be less, 10, 5, 1.5. But it's the first time that you can make these kind of statements without assuming an underlying model. Okay, let me show you another example. And that relates to a, well, controversy or debate whether or not it's possible to reach Carnot efficiency at finite power. Pre-2011, I would have thought, no, that's impossible. Carnot efficiency requires quasi-static motion, i.e. infinite cycle time, i.e. no power output. But then there was this beautiful PRL by Casati and Giulio Benenti and Keiji Saito, who pointed out that in systems with a magnetic field, where the Onsager symmetry of the off-diagonal elements of the Onsager coefficients is broken, that in such systems, if you just use this 60s style linear reversible thermodynamics, you find that it might be possible, or it's not excluded, to have Carnot efficiency at finite power. I found this surprising. I thought there must be some additional effect which will prevent this. But now and then there were quite a number of papers, and using the uncertainty relation, we could understand these various case studies now in the following way. In the steady state case, power is a current. So we apply the uncertainty relation to this work current, which is power. And now the entropy production can be related to the exchanged heat. And then if you play a little bit around, you find that the power is less than the linear distance of your true efficiency to Carnot efficiency. So if you just look at the round bracket here, you would say that power has to vanish universally, at least linearly, as you approach Carnot efficiency. However, there is this amplitude dW, which are the fluctuations in the power. the corresponding diffusion coefficient. So you see that if these fluctuations blow up, there is in principle the chance that you reach a finite limit. And that explains many of these case studies which have been invented. So there is a trade-off not just between power and efficiency as we thought previously, but between power, efficiency, and constancy. And again, this is a very general relation that is just based on assuming a Markovian description. Okay, so the next question, of course, is let's stay within a Markovian, but let's leave this realm of non-equilibrium steady states. And then the first class, of course, is periodic driving. And we knew from with work with Andre that in general, the thermodynamic uncertainty relation fails. So if you drive the system periodically, you can get a higher precision at a lower cost. For time symmetric protocols, there was a nice bound by Pressmans and the late Chris Vandenberg. And then there were quite a number of what I would call technical bounds, which are, mathematically correct, but useless since you don't have access to these quantities. And we found with my grad student, we found a relation which I will describe later in a more general way, which I think is operationally accessible. The second class of systems, you might be interested in relaxation towards equilibrium or towards a non-equilibrium steady state. And there were also relations valid now for this situation. So let me describe the result with Timur Koyuk, which generalizes and comprises many of these previous relations. So we allow general time-dependent driving, i.e. we allow rates which are time-dependent. So they depend on an experimental parameter lambda, and we assume that this lambda parameter can be experimentally changed faster or slower. And we observe the system for a total time t. And then the generalization of the tour is the following one. J is the mean current now observed for a fixed control speed v and a fixed time calligraphic t. dj is the corresponding diffusion coefficient. Sigma is the corresponding entropy production rate now averaged over this time-dependent process. And this is the old relation except for this delta J term. So there's an additional term which says how does the mean current change with the observation time and how does it change with this experimentally speed parameter. Again, all of this is experimentally accessible. So let me show you two illustrations of this more general relation. So the kind of paradigm is typically a driven tap particle. So we start with the particle in a harmonic trap, and then at time t equal to 0, we start moving that trap at velocity v. And then we can look, for instance, at the finite time mean velocity, which of course is just the distance covered divided by the time. Or we can look at the finite time applied power, which would be essentially force times distance, or the dv d lambda more precisely. Now we are measuring these experimentally accessible quantities, and we look, for the rest of the talk, I'm plotting the uncertainty relation, putting this on the other side, and I call this the quality factor. So this will be a quantity Q, which is bounded by 1. And here you see now data. So the solid lines as a function of the observation time shows you the quality of this generalized tour for different stiffnesses of the spring based on measuring the velocity. Or if you measure the power, these are the dash data. So and again, you can evaluate, or experimentally you could evaluate these quantities, for instance, without knowing the stiffness of the trap. You just measure the velocity. And what you find is you would recover, depending on in which regime you are, you would recover something between 40 and 80% of the entropy production. Again, in a model-free way. You don't need to know the stiffness. And perhaps as an even more convincing example, let me come back to this experiment I introduced earlier. In these experiments, often people also apply a force ramp. So the force becomes time dependent. I'm almost done, Roberto. And if you now just ask, what is the state of the system in at the final time? This is, I call little a. Or you ask, how much time did the system spend in a certain state, let's say in the unfolded state? You have again this relation, which you can evaluate just based on your experimental data. And here are these quality factors. So you see, depending on the observable you use, again, you're able to recover something like at the maximum 80% of the entropy production in this process without assuming a model, just by observations. And you can, you can observe cross-grade variables. You don't have to observe the mesostates individually. Okay, let me just on one slide, I think that's the last one, briefly mention where we now, which situations which go beyond the Markovian regime. So we know that for underdamped dynamics, it fails for finite time. We believe that it's true in the infinite time limit. As far as I know, no proof yet for underdamped dynamics. We know that we can break it with a magnetic field. We have applied it recently to stochastic field theories like the KBZ equation. I should mention there is a number of more generalized relations which typically get very bad if you go to the infinite time limit. And of course, it's now really a strong activity to look at this in quantum dynamics. These were 5 of the very early papers, and I don't think a complete picture has been reached yet. Thank you very much. Thank you.
Thank you for this very nice talk. There is space for some questions, please.
You mentioned the possibility to reach the Carnot limit at finite time for system with magnetic field. And but there is some intuitive physical reason apart the computation. There is some intuitive argument, or just manipulation.
I mean, it's a kind of simple manipulation. What Casati and co-workers did, just based on this matrices, linear irreversible thermodynamics, and then you find that when the ratio between these off-diagonal elements.
No, this I understood. No, yeah. But there is some intuition why with magnetic field is possible, without not possible.
No, I don't have an intuition, but we know that even with the magnetic field, for instance, if you do, this is work with Kai Brandner, if you look at an n-terminal situation and you use this Landau-Büttiker scattering approach, you can show that again, you would need infinitely many probe terminals. So we have bounds as a function of the number of terminals. So to come up with a clean realization, I think that's still impossible. You can reach it in certain limits. Saro Fazio did work with Michele Campisi, looking at the phase transition as the working substance, which exactly is this kind of situation where the fluctuations blow up. But I have no simple intuition about it, Angelo.
There is space for a very quick question, if there is anyone.
No, so my question is about the non-Markovianity.
Yes.
So in this list, the Markovianity, non-Markovianity is in the item of stochastic field theory, right?
In the items
of stochastic field theory, there you have.
No, I mean well, the underdamped dynamics is already non-Markovian if you look at it from the perspective of just the position.
Okay.
So there the diffusion matrix is singular, and therefore this proof doesn't work.
Okay. Thank you.
Actually, the stochastic field theory I should not mention under the non-Markovian case.
So let's thank again Udo for the very nice talk, and we can go to the following. Is actually online. You change the order? Okay. My next speaker is Neri Meraf from Technion. And he's going to speak about work instruction and production in information-driven finite state engines. I want to remember the speaker that he has 25 minutes for his talk and 5 for discussions.
Thank you very much. Can you hear me okay?
Yes, we can hear you.
Okay. So I'm not a physicist. I'm actually in an electrical engineering department, and my field is information theory. So I come to the problem area of information thermodynamics from the side of information theory, and I want to discuss some relationships between entropy production and work extraction in a model of a finite state engine, which is also a conventional model in electrical engineering and in computer science. So when we talk about information thermodynamics, there has been a series of works around this subject, some renaissance of the early works by Maxwell and Szilard that I mentioned in a few minutes. But the common theme of all of them is that the presence of information in a physical system apparently, seemingly violates the second law, because there's an extra term associated with entropy change of the informational ingredient. And I would say that the research in this problem area can be roughly categorized into 2 main categories. One of them is about systems with measurement and feedback control. And I've listed here only a few works on this from the last decade, and not a completely non-exhaustive list, and also it doesn't include all the works from the last few years. But the point is that we continuously measure the system and create feedback, and the information is in the measurement. And the second category is the systems with so-called information reservoirs, in addition to the heat reservoir and the system itself. And there we are talking about either on a memory device or a digital tape, where the sequence of bits or symbols sequentially interact with the system. And I'll focus on that later on. So going back to the good old Maxwell demon from about 150 years ago, we all know that we take a volume with gas and put a barrier in the middle, and we open the door from left to right whenever we encounter a speedy particle, and we open it in the other direction whenever we see a relatively slow particle. And at the end of the process, we have all the speedy particles on one side and all the slow ones on the other side, and we created a temperature difference, thereby seemingly violating the second law. The Gedanken experiment of the well-known Maxwell demon. And about a few decades later, Leo Szilard came up with his engine with a single particle. You put a barrier, you measure in which one of the parts of the system it appears, and then you can extract work by letting this particle push the barrier, and then you complete the cycle by removing the barrier, and it looks like you're gaining work without investing any energy. And there's, of course, an extension of the Szilard engine to a situation where the barrier is not necessarily in the middle, and the measurement Y is not necessarily clean, it might be noisy. And then the well-known result by Sagawa and Ueda from 2011 is that the maximum work you can extract is proportional to the mutual information associated with the channel from the real position X to the measurement Y. And several years ago, together with a colleague and a student, we have used this relationship in the context of gambling. In general, the system with measure-oriented feedback is a closed loop where we have a thermodynamical system. We look at its state xt at time t. There is a noisy channel by which we take the measurement. We get yt. And on the basis of yt and its past, we create the control and feed it back to the system. And what the two Japanese physicists, Sagawa and Ueda, have shown us is that in the well-known inequality that relates extraction to work and a change in the free energy, there is an additional term which is proportional to the mutual information, just like I've shown before. And in fact, it is more exact to say that it's not, in general, it's not quite the mutual information, but what is the so-called directed information, which is well known in information theory as a related notion that takes into account also causality. And the interesting point here is that we see here the directed information denoted here with an arrow in the context of feedback, and it's well known that information theory too, the capacity of a channel with feedback is in general given by the directed information and not the mutual information. So there's an interesting relationship here between information theory and physics. A few years, about a decade ago, almost a decade ago, there's a well-known paper by Mandel and Jarzynski, which looked at a system with the second category that I mentioned, an information reservoir, which is a tape of bits that interact serially with the system, in this case, a wheel that lifts a mass. And the mechanism is here, that period of length tau, there is a Markov jump process where the initial state is exactly the content of the current bit. And there is transition back and forth from state 0 to state 1, as we see here in the diagram, where in state 0, I can only make a half cycle counterclockwise. And when I'm state 1, I can only move clockwise. So only the blue arrow can lift the mass, while the red arrow causes the mass to descend. So the overall work done by the system depends only on the parity of the number of transitions. And they show that overall, the maximum work that you can extract from the system is proportional to the difference between the entropy of the outgoing bits. I forgot to mention that the final state of each period of length tau is recorded on the outgoing tape. So eventually a 0 can turn to 1 and vice versa. So the entropy of the outgoing sequence in red might be different than the incoming sequence. And the difference in entropies is an upper bound on the work that we can extract, or it can be put in form of the second law, that the total entropy, including the informational ingredient, must be non-negative, total entropy change. And the more in the later works with Defner and Jarodzinski, there's also with a memory device instead of a tape, and they show an extended version of the second law, where we have the change of entropy of the device plus the change of entropy of the heat reservoir plus the change of entropy in the information reservoir cannot be negative. So much for history. Now I'm going to talk about a slightly more general model that I developed a couple of years ago on the basis of some earlier work by Boyd, Mandel, and Crutchfield, I think. And it looks in the same spirit. We have certain ratchet that is fed by an input tape. And there's also, like before, an output tape of bits written. And there's an internal state variable, which I denote by S of n, which is updated by the mechanism of the system. It interacts with a heat reservoir and also with the machine. And again, we have state transitions, and the energy level depends on the height of the mass. We have here two levels of random processes. One is the higher level process is in discrete time. It's the process defined by the incoming bits x of n, the outgoing bits y of n, and the state variable n. And the discrete time is in multiples of a single period of length tau, as before. And this is the higher level process. The lower level process is within each period of length tau. It's a Markov jump process with two components, psi of t and sigma of t. And the initial state at each period is xn sn, the current input and state. The final output and the state are recording the final values of the pair x and sigma. And the process within each period of length tau is a Markov jump process with state transitions according to the energy level, assuming detailed balance. So for this model, Boyd, Mandel, and Crutchfield have argued that the asymptotic normalized work, the work divided by n, where n is the number of cycles, is proportional to the entropy rate, namely the normalized. Here I'm denoting, I forgot to mention that I'm denoting the entropies by H, which is the information theoretic notation. So the entropy rate of the output process minus the entropy rate of the input process, assuming, of course, that both input and output are stationary. And I have personally, I have several reservations regarding this paper. I'm not going to get into it deeply here in the details. They all appear in the paper. But let me just say that I've re-derived results for exactly the same model with the following things that I can say about it. First of all, the approach is very simple and rigorous, and very mild assumptions only with two S's. And rather than asymptotic results, the results that I have are exact for every number of cycles, capital N. The bounds that I'm getting are relatively simple to calculate and potentially tight. I'll discuss it. And in contrast to their result, here the state variable also will play a role, as you will see shortly. So the basic idea comes from the well-known inequality known for Markov processes, that the Kullback-Leibler divergence between the instantaneous state distribution, P of tau, and the equilibrium distribution is monotonically decreasing in time. Here, Cover and Thomas is just one reference for that. There are plenty, of course. So at every positive time tau, including the final time of each cycle, the divergence is smaller than at the beginning of the cycle, where it's P naught. So if the equilibrium distribution is the canonical one, and we plug it in this inequality, we obtain right away an inequality concerning the energy change or the work that you can extract in terms of the difference in entropies. But here it's not the same as before. Here, these are entropies that involve not only the input and the output, but also the state of the system, as you can see. And that's a big difference. And this was for one cycle. When I'm summing up everything over all capital N cycles, we obtain this form, which can also be presented as the production of the entropy, conditional entropy production given the state. Namely, it's the entropy production beyond the past of the system. Whatever the system remembers from the past is encoded in the state. Plus a term which is the entropy production of the state itself. So if the number of states is finite, then the second term is relatively small because it's bounded by a constant independent of n, while the first term roughly increases proportionally to capital N. So we have this relationship. There are a few comments about it. First of all, it is tight in the sense that I can construct a system which meets the bound arbitrarily closely in the spirit of the idea of a quasi-static process. I'm going in small steps, so I can get, if the equilibrium distribution is sufficiently close to the initial one, then the ratio between the actual work I can extract and the entropy production in that cycle is very close to 1. And if I'm going in small steps, I can get as close as I wish to the bound. The details are in the paper. I'm not going to get into it now. A few comments about special inputs. First of all, for a memoryless input, where the conditioning on the state is immaterial, the inequality is of getting this form. We have the sum of differences of unconditional entropies plus the entropy production of the state minus the mutual information between the state and the output. So we are losing something if the input is memoryless, but the machine has memory, namely it has a non-trivial state, then we are losing something from possible dependencies between the state and the output. So the best thing we can do with memoryless inputs, asymptotically, neglecting the entropy production of the state, which is finite, it is best to process memoryless inputs by memoryless machines, which is quite intuitively appealing. For a Markov input, we have the pair xn sn is jointly Markov, and then we can, if it has a stationary distribution, then we can write the joint distribution of all 4 variables. where S is the current state and S prime is the next state. And we can compute actually everything, both the work and the entropy production, just from this joint distribution. This is a lot easier than calculating the difference between entropy rates, as in the result that I mentioned before by Mandel, Boyd, and Crutchfield. In the case of a Markov input, the output of the system is a hidden Markov model, and it doesn't even have a closed form expression, only bounds. A word about conditional entropy bounds. It turns out that if I define any function of the past, which includes the past inputs, the past outputs, and the past states, then I can write an inequality of entropy production, of conditional entropy, or entropies. But it is quite disappointing that the best choice of this Vn, or the function Fn, is simply null, namely condition of nothing, which is leads us back to the basic result. However, if we look at it not as an upper bound on the work, but as a lower bound on the entropy production, then we can get a nice lower bound on the output entropy in terms of the input entropy and the work. So if we have any way, if we can compute easily the right-hand side, then we have a nice lower bound. Finally, I want to mention, I think I'm almost out of time, right? An equivalent result in the more general, the information inequality that I started with, the motonicity of the divergence for a Markov process, holds not only for the usual Kullback-Leibler divergence, but also for F divergences with any convex function. So here's another set of inequalities I define, which is written somewhat differently. I am looking at the quantity which can be thought of as the negative free energy in units of kT. Okay, so this is the negative free energy at the beginning of the cycle. This is at the end of the cycle. So the negative information, the negative free energy is increasing, which means that the free energy is decreasing. This is one way to present the earlier result that I talked about. But now, when I'm replacing the logarithmic function of the divergent by a general convex function, Q, I'm getting generalized inequalities associated with the free energy before and after the cycle. So for certain specific choices of the convex function Q, I'm getting certain interesting inequalities. Two of them are associated with the characteristic function of phi, where the parameter z is in one case in the interval between 0 and 1, and in the other case outside the interval 0 and 1. And then the direction of the inequality is reversed, which is kind of interesting. So let me conclude. We have seen simple relationships between work and differences in entropy, namely generalized second law. The bounds are potentially tight in the sense that we can approach them if we are willing to make enough effort. The memory of the past of the system is encoded in the state, and we have also a term that is associated with the entropy production of the state. The bounds are relatively easy to calculate. There are examples in the paper. And as a last bonus, we also have a lower bound on the entropy of a hidden Markov model. That's about it. Thank you very much.
Thank you for the nice talk. There is space for some questions. No questions? Okay. Well, there are no questions from the audience, so thank you again, and we can go to the next speaker. Have to wait for? No? Mr. Linak.
Yeah, I'm around.
Yes, yes. Okay, fine. So we have now the final talk of this morning, which is given by Estelle Inak from Perimeter Institute in Canada. So she's going to speak about variational neural annealing. Please, you have 25 minutes and 5 minutes more for discussion.
So let me share my screen. Can you see my screen?
Yeah, what we see, okay, fine, it's okay.
Okay, one second, I cannot see myself. Okay. All right, thank you very much for the opportunity to present my work. I would have loved to be interested. I mean, I did my diploma in ICTP and my PhD at SISSA and ICTP. So it would have been a pleasure to be there, but unfortunately I can't. But I want to thank the organizers for the opportunity to present my work. I'm going to talk about variational annealing. It's a work that we put on archive in the beginning of this year, and it was recently accepted in Nature Machine Intelligence. So typically when we talk about annealing, what we have in mind is actually solving optimization problems. And optimization problems occur in both in science and in different places in industry. So here I gave just a couple of examples. The so-called traveling salesman problem, which is a problem of finding the shortest path for a traveler going through a certain number of city walks. Here you have a problem that is typical in quantum chemistry. For example, you have atoms interacting with a certain potential, and you look for configuration that minimizes free energy. That is so-called protein folding problem, the problem of finding native state of protein, or for example, a portfolio optimization problem, how you should best invest, say, for example, the stocks you have in your portfolio. And there are many more of these. So why are these problems interesting, especially for us as physicists? Is because they could be cast into a form that we understand, which is the form of a classical Hamiltonian, right? Where the interaction between the spins uniquely encode the optimization problem that we have at hand. And solving that problem is actually equivalent to finding just the ground state of this classical Hamiltonian. However, from inside, from say, disorder systems in classical disorder system theory, we know that there are some problems that are notably very hard to solve. For example, disorderizing glass in the random longitudinal field value ground state descent cloud. So usually when solving optimization problem, we relax our initial aim of finding the exact solution, but finding an approximate solution. So that's where heuristics come into place. It's very good to visualize this kind of Hamiltonian as if an energy landscape over some sort of configurations, right? For hard problems, it's very good. Exponentially, it has an exponentially large number of minimal or solid points. And you need, with your heuristic method, to design an efficient search algorithm to find, if not the deepest value, like metastable value that are close to the deepest one. So a famous method that was used, okay. Oh yeah. A famous method that was used in searching for this approximate solution is a so-called simulated annealing method that uses thermally activated process to overcome the barrier in the search of the deepest value. And it's actually inspired by a very old metallurgical technique, whereby by making a material, say glass, more solid, you have to heat it up at a very high temperature so that you give enough kinetic energy for the atoms to explore different configurations. And then you slowly cool it down so that the atoms themselves in the material are arranged in configuration that minimize the frame transfer. And this kind of concept has been actually implemented on dedicated hardware. Another paradigm is inspired by quantum mechanics, where instead of using thermally activated process to overcome barriers, you could just tunnel through them by using the so-called quantum tonic effect. And that gave rise to another heuristic method called quantum annealing. And this has also been realized on dedicated hardware. So typically for this direct machine, for example, which is a quantum annealer, there are techniques that have been used to benchmark, first of all, how quantum it is and whether it does provide some sort of quantum advantage to solve optimization problems. And most of the techniques that have been used to benchmark it are actually Monte Carlo methods. And there is a zoo of Monte Carlo methods, both classical Monte Carlo method and quantum Monte Carlo methods, simulating respectively classical annealing and quantum annealing. Right. But the purpose of these slides is actually to show that, or to remind us that initially Monte Carlo methods were designed to simulate equilibrium properties of classical system or quantum system, not for annealing, right? And so we took the inspiration from very recent methods that were built for machine learning that were actually also used to simulate equilibrium properties of both classical and quantum systems. And this use neural networks, especially this seminal work by Kalia and Troyer, where they use the supervised Boozer machine, which is a specific kind of actual neural network, to probe the properties of quantum mechanical systems. These neural networks or these methods were based on variational principles that estimate the equilibrium properties, and neural networks were used as variation ansatz. So idea is to actually repurpose this kind of methods to actually emulate. So we asked ourselves whether we could repurpose this method to emulate actually the annealing paradigm in the variational framework, both classical and quantum annealing. So next, I'm gonna explain the bedrock of that method, which is based on the so-called variational Monte Carlo method. So the VMC method is a quantum Monte Carlo method that is used to simulate properties of quantum system at zero temperature. It also, by having a good guess of what the constant wave function ansatz will be, and it minimizes the so-called variational energy, which is this quantity here. So irrespective of the ansatz that we choose to represent the constant wave function of the Hamiltonian, this quantity always gives an upper bound to the exact constant energy. And in practice, it's just computed by using the statistical average, where the spins are sampled according to the absolute value square with the distribution. And so there's no sign theorem, intrinsic sign theorem in VMC. And next, how do you update the parameters of your ansatz is simply by following the gradient. So you have this exact formula of the derivative of the variational energy with respect to the variational parameter that is given by this, and you just replace the quantum the quantum expectation values by the statistical one, literally. And you choose whatever flavor of optimizers to update your parameters, either stochastic gradient, same way to stochastic confusion Adam. But also we use Adam because it was better for neural networks using TensorFlow. Right. So next, which kind of ansatz did we use? As you guess, we use actual neural networks, but there are so many different actual neural networks. So which one? We chose actually neural language models. These are models that are used in neural language processing. They're powerful probabilistic models that are able to capture correlation between words in natural language. And for example, giving a word is able to predict what the next word is. And it has so many applications, one of which I believe all of us, most of us are familiar with, is syntax completion. For example, I'm sure when writing your email, you've seen like Gmail suggesting how to complete the sentence. Right? It's because there are powerful neural networks behind that have learned the correlation between words in English or whatever French, what they're using. So a high-level explanation of how this could be done with recurrent neural network. And let's say you're writing an email, you have the names of the people you're writing to and the subject of the email. You give it to an RNN cell and it predicts what the first word of your email is going to be in this field. So in this sense, it has learned what is a conditional probability distribution of sampling the first word given a name. And it uses that first word as an input to sample the next word, and so on and so forth. So here it has learned the second conditional probability distribution. So if you keep on going, you've learned a bunch of conditional probability distribution, and if you multiply them with the chain rule of probability distribution, you have basically learned the probability to sample the first sentence of your email given an input, right? So how does it relate with us wanting to solve optimization problems? So say you want to sample a spin configuration, which hopefully will be the result, say, of an optimization problem. We could use the same sampling, which is autoregressive sampling, to literally sample each spin of our configuration one at a time, and using again the chain of probability distribution to actually obtain the joint probability distribution of sampling as spin configuration. And if you're interested in a wave function, we just do square root of it. So this is how we can use these powerful neural networks that are used in natural language to actually encode the state of a quantum system. The H here is called the hidden state. It encodes information about the previous spin. I give more detail a little bit later. And the way in which this autoregressive sampling is there a question? Okay, that's probably not a question. So the way in which these samples are generated, they are generated exactly. There's no autocorrelation time compared to if you had to build a Markov chain, for example, right? You always have a correlation time. And for us, since we're interested in solving like these other systems of system, for example, I mean, you imagine that the autocorrelation time the Markov chain we for very, very long, especially as we increase the system size. So we kind of avoid this problem by using this kind of ancestral sampling here. So this is one of the reasons why, for example, we didn't use something like Russell-Boltzmann machine, convolutional neural networks, or graph neural networks, as another. We prefer to receive neural network. Another reason is that by consumption, the wave function we probably see is normalized to unity. And as we see, it will be very useful to compute some quantities that will otherwise be kind of impossible to compute. All right, so next I will tell you what this RNN cell is that we use in our work. We use the so-called tensorized RNN cell, which has this recurrent form, and this is kind of the architecture that we use. Here, the T is a tensor, which is that's parameters that we need to optimize or to train. Beta is also a variable that we need to train. And this is the traditional recurrent relation, let's say, for the valina RNN, where you have the weight and nucleus here. So the reason why we choose this is a little bit inspired by tensor networks or NPS, is that here we have a local Hubble space that interacts with the hidden state in a very compact way. And also we have this non-linear activation function, whereas in the vanilla RNN, you just have a concatenation of them and they only interact via, some sort of non-linear activation function. So we saw that, that this representation is more compact and it has a higher representational power than just using vanilla RNN. And to check that, we compare with the simulations on the quantum chain. And we look at the variance of the local energy. The lower it is, the more accurate your results are. And we compare vanilla and then respect to tensors, and at the critical point. And we saw that it gives better result. And we also benchmark with some more sophisticated version of RNNs like GRUs for those who are familiar with LSTM. And we also find tensor RNNs. So next, for randomizing chains or for systems, local problems that we look at that have disorder. For example, the random coordinates chain criticality, we saw that using the so-called no-weight sharing, that at each lattice point, each time we generate a spin, we use a different weights and variances. Basically, we saw that it is, this is way much more accurate than sharing the weights across the lattice side, which is what's typically done, for example, in machine learning. So we use no sharing for this other system. And for long-range interacting system like the so-called Sherrington-Kilpatrick spin glass, we use a more sophisticated neural network architecture that use skip connection. They were introduced in machine learning to deal with the vanishing gradient problem, but here we saw that it is accurate to capture the long-range correlation that we have in our problem. All right, so next I need to go faster. All right, so I talk about the quantum annealing algorithm. So what we do is that we want to prepare the system into an Hamiltonian that is easy to prepare. All the spin point in the x direction. We initialize the RNN with random Wilson biases, and to prepare the system, we just do gradient descent step. And here we land on the initial ground state, right? And next we do an annealing step, that is we change the transverse field, we reduce it, and we introduce a polar Hamiltonian. That makes us to shoot out of the incident ground state, so we need to fall back on the incident ground state. So we have to perform some gradient descent step. And then we are again on the incident ground state. So we change again the Hamiltonian and we fall back again on the incident ground state, and so on and so forth. We reduce the quantum fluctuations so that at the end, when all of them have been removed, we expect to find ourselves in the ground state of the polar Hamiltonian. And we came up with a theorem that tells us the number of sufficient number of gradient descent steps that we need to remain adiabatic, that is bounded by both the inverse of the gap, minimum gap, and the inverse of the minimum gap squared during the annealing. For the variation of classical annealing, the cost function is different. It's the variation of free energy, which is the expectation value of a polar Hamiltonian over a variational state. And then we have a time-dependent temperature, here is linear, with this von Neumann entropy. So this von Neumann entropy is estimated with the RNN. And if the RNN was not normalized, it wouldn't have been possible to estimate this thing efficiently. So that's one of the reasons why we chose like autoregressive neural networks. So next I will present some results on the randomizing chain. This is the Hamiltonian. We look at this quantity, the reserve energy, which is a difference between the expectation value of this Hamiltonian at the end of the annealing minus the exact one for different system size. At the end of the annealing, we generate 1 million samples with the neural networks, and we look at 25 disorder realizations. And we see that when we look at the reserve energy per spin, we expect the number of annealing step. At short annealing step, we mean like we're doing kind of a quenching, either thermal or quantum quenching. We see that variational quantum annealing is superior. But at long annealing times where we are more adiabatic, we see that VCA is superior to VQA. And this is in contrast to what was observed in this paper, where they actually simulated annealing by using Monte Carlo, classical quantum Monte Carlo, and they saw that wait, oh my God. So they simulated annealing, both classical and quantum annealing. No, they use a master equation for classical annealing, and they did the exact simulation using Bogoliubov division equations for quantum annealing. So not Monte Carlo. Yeah, and yeah, for the simulations, quantum annealing was superior to classical annealing, which is contrary for us here. And basically for them, simulated annealing and also quantum annealing, the real-time dynamics had a logarithmic scaling on this problem, but for us, we have like a polynomial scaling. So we do see an advantage of this kind of neural annealing procedure. So next we have a result on the 2D on the spin glass. We did use a different RNN autoregressive sampling that encodes kind of a snake-like sampling that encodes like the 2D architecture of the spin glass. And we saw that here again, VCA is superior to VQA, that the blue data is superior to which data, to the green data here. Another interesting thing is that when we decide, we wanted to benchmark whether annealing was actually relevant here. So we directly optimize like this polar Hamiltonian. So we look at this red data just for respect to the number of gradient descent step, and we see that as we do train the neural network, the reserve energy decreases, but it's order of magnitude very far away from what we do with annealing paradigm encoded. So we do see that doing annealing is important here. Since VCA was superior to VQA, we benchmarked it against traditional heuristics, simulated annealing, simulated quantum annealing, and we saw that at long annealing time, VCA can be like up to 100, like here is 3 orders of magnitude superior to both simulated quantum annealing and simulated annealing on 1600 spins. And next, you have the Shannon quadratic model. And also here we see that VCA is consistently superior to simulated annealing and simulated quantum annealing. We did, for the check, we look at the last data points. We do an histogram of the solutions. We have 25 data points here. And we see that, yeah, VCA also finds solution more often than simulated quantum annealing, and SA that stock often to local minima. And when we look at the probability of success for each disorder instance, which is the ratio of the number of spin configuration that actually find the ground state with respect to the total number of configurations that we had, we see that except for one instance, VCA finds all the solution compared to the other ones. So yes, with this, I conclude that we've seen that annealing search in the variational space seems to outperform the search in the configuration space, that VCA is more efficient than the variational emulation of quantum annealing, and is more efficient than the traditional simulated annealing and simulated quantum annealing. And we advocate that it could be a good candidate to solve reward optimization problems. And yeah, we've seen that neural network are powerful and that for VCA and VQA, and they tend to depend on the kind of Hamiltonian that we have, the architecture. And with this, I would like to thank my collaborators, especially Mohammed, who is the one who has designed all the neural networks. And I'll be happy to take any questions if you have.
Thank you very much, Estelle. A special thank to this last speaker also because she accepted so kindly to give a seminar at 6 a.m. local time in Canada. So it's quite an early time. Are there questions?
Hi, Estelle. I'm Andrea Gambassi. Hi. So just have a question. Probably you mentioned it, but I'm not sure I got it. So as you are saying, VCA is more efficient than other methods because, I mean, computationally speaking, how is it doing? So, I mean, you can determine better the ground state energy or whatever, but in terms of cost. Compared to the other methods.
That's a good question. In terms of computational cost, is actually, let me try to remember. Is actually cost effective compared to variational quantum annealing. Is running faster. It has a beta scaling as well. But compared to simulated annealing runs very fast, like maybe in practice, how would I say, maybe 100 times faster. But the point is that even if you run it forever, for example, here, if you keep running it, you are not going anywhere, right? So, yeah, the computational cost of
what is the cost of each run? Is it the same, or one requires much more computation than the other? So that
So SA runs very fast for sure, but the point is that even if you run it, so the scaling is what matters, right? So even if you run it for long, you are not going to go anywhere, right? You will still be, stuck in local minima, for example, for here. Right, but so variational classical annealing and quantum annealing, we run it on GPUs because you have to use neural networks, and we have to use all the inbuilt advantage of being able to do, for example, backpropagation in an efficient way. Right? Simulated annealing and simulated quantum annealing, we run it on just one single laptop. So.
Okay.
Yeah.
Okay. Thank you.
Welcome.
Are there other questions? If not, we thank again Estelle for this kind talk, nice talk, and all the speakers of this morning session. And let me recall that people in presence are probably supposed to have a photo, group photo now.
Facciamo.
Io proporrei di fare una qui davanti.
Ok.
Possiamo fare fuori la foto? Se vuoi possiamo fare fuori. Fuori, come è?
sì, ci dobbiamo mettere dove fuori però? Sulle scale della SISSA?
Sì, sì.
Vabbè, ci mettiamo nelle scalette che vanno giù verso la nuova SISSA.
Qui nell'entrata.
Ma siamo un po'... Udo, don't run away.